Welcome everyone, this is Michael Gibbs from Go Cloud Architects. If some of you could let me know if you can hear me by signaling with say, I'm here or I can hear you. Okay, wonderful Leonard, thank you for letting me know. Welcome everyone, my name is Michael Gibbs and I'm the founder and CEO of Go Cloud Architects, and we are dedicated towards building high performance cloud computing careers. I've been working in technology now for well over 25 years, 1993 to be exact, but I don't like talking about it because it makes me feel old. So I've been working in tech now for 25 years. And one of the things that I've done for well over 2 decades is I've worked with people to help them find their first tech jobs, get promoted in tech, and there's no better feeling, let me tell you, after 20 years of helping people find their first jobs, is when you get that phone call and someone says, guess what? I've got my first tech job. So this is something we've done forever and it's near and dear to our heart and it's our complete and total mission. So what we're going to talk about today is this following. We're going to be discussing the AWS Advanced Networking Curriculum. Now, I want to let you guys know we're going to cover this from an architecture perspective. And the reason we're going to cover this from an architecture perspective is we're architects. So we're going to talk about the network from a system design perspective, how the pieces and parts work together, how the network is necessary for putting the architecture together. The network may be the most critical thing you actually learn in your entire cloud computing career, and here's why. The cloud is nothing more than a virtualized network in a data center. And if the network doesn't work, nothing works. I mean, literally nothing works, and I can tell you this from a lifetime working in data centers, networking, and cloud computing. So the network is dear and dear to my heart. You should always, always, always listen to the source of information prior to actually making any kind of, what's the word I'm looking for? Prior to actually determining, the source of information. So I'll let you know a little bit about me. I am one of the original Cisco certified internet experts. Back when it was a 2-day test 20 some years ago with a 90% failure rate, I was one of the first Cisco certified internet experts. In fact, my number is 7417. So to put it into context, I've been doing this networking thing for a long time. The format that we're going to use for this bootcamp is as follows. We're going to have approximately 20 minutes of discussion, 10 minutes of questions and answer, 20 minutes of discussion, 10 minutes of question and answer for the remaining time. The format will be 12 p.m. to 3 p.m. Eastern Standard Time, Monday through Friday this week. You will periodically hear from me, and what's going to happen is it's a pretty big interactive group, and it's going to be really hard for me to really go through the comments. So what's going to happen is Chris from my team is going to be looking at your comments. They're going to be aggregating, bring up questions. He's going to be sending them to me on Slack, which is another way, and I am going to be answering questions as they occur. So super excited that you're all here. Let's go start to have some fun. So as we begin today, we want to make sure we give you the fundamentals, because what we're going to do is we're going to start slow and we are going to ramp up really fast. So we're going to begin with what is networking. Then we're going to talk a little bit about the structure at AWS and how their cloud's organized. And then we're going to gradually ramp up. But when we do this, we're going to assume that you know nothing. We're going to do this because there's a lot of network engineers like me that want to move to the cloud, and we want to know that you are solid with cloud knowledge. You might come from another cloud and not this cloud, so we wanted to make sure that you know the AWS cloud environment as we're doing it. And we want to make sure that at any time you're good and you're good to go. So ask us any questions anywhere and we'll answer them. I want it to be as much like a classroom experience, so anything we can do, let us know. Periodically, if you're enjoying this conversation, please leave a like or some comments, just because it helps us know that we're doing a good job, because everything we want to do is to take care of you all. So what is networking? Let's begin from the beginning. Networking is simply the connecting of multiple computer systems. If you've got one computer and you wanted to talk to another computer, you need a network. So that is networking. Networking, for people like me, look at it as plumbing. Realistically speaking, networking is the set of plumbing that enables your systems to talk to each other. What is networking? Networking is going to include the following components: your routers, your switches, your cabling, and your LAN and WAN connections. This is real networking. Now, in the cloud, there'll be some logical networking, but it is pure networking is routers, switches, cables, and LANs and WANs. And welcome to you all that are there. So what does networking look like in action? Now, if you're a network engineer, some of this is going to be reviewed, these first couple of slides. But if you're not, we want to make sure you get it. So please bear with me. We're going to show you what networking is like. At the high level, this is really networking in action. Let's say you've got a system, and we'll walk through how all these things work throughout the training program, but let's look at this graphic that we have here. We have two PCs. We have PC1, which is identified by its IP address of 172.16.1.2, sitting on one subnet. Now, if this PC wants to reach PC2, which is on the 172.16.5.9 subnet, /24, the PC can't reach it. The PC can't reach it because it's not on that network. So what will ultimately happen is that the PC wants to reach something that's off of its network. The PC is going to look in its routing table. So PC1 is going to look at its routing table and say, do I have a route to get to 172.16.5.0? And the PC is going to say no. So what will happen is the PC is going to look in its routing table and say, but I have a default gateway, which is a route that basically says, go to this router if you don't know where to go. So PC1 on the way to PC2 will say, let me send my packet to router 2. Now router 2 is going to do something interesting, and it's going to look in its routing table and it's going to say, do I have a route for 172.16.5.0? And if the answer is no, the packet gets dropped and everything is done. Now if the answer is yes, then things are really great. And ultimately what's going to happen is the packet will be sent out the interface that's next closest. So in this particular case, router 2 is going to say, I can't reach it, but I know that router 3 can reach it, so let me send my packet out Ethernet interface GE0/0 to router 2. Now router 2 is going to look at this and say, do I have a route? And if router 2 has a route, it'll send it. If it doesn't, the traffic will be dropped. Router 2 is going to say, yes, I know how to reach 172.16.5.9. Send it over to router 3 over Gig and Ethernet 0/0. So the next thing that happens is router 3 says, I have a route to the subnet. It's directly connected. So this router will do something called an ARP. It'll send an ARP broadcast, which is who has this MAC address for 172.16.5.9. PC 172.15.5.9 is going to respond to this ARP who has with I have this MAC address, and then the PC will respond to the router, and then the connection will be established. Now, because PC1 sent information to PC2, PC2 is going to answer it and say, yes, PC1, here's the answer to your query. And this is going to happen by PC2 is going to say, do I have a route to PC1? And it's going to say, no, I don't. And because I don't have a PC route to router 1, what it's going to do is it's going to look in its default gateway. And it's going to say, I have a default route to router 3. So now router 3 is going to say, do I have a route to PC1? And router 3 is going to say, yes, I do. I know how to go to PC1. I'm going to go through this interface and I'm going to drop it off at router 2. And then router 2 is going to say, do I have a route to PC1? And it's going to say, yes, I do. Send it to router 1. And that's what's going to happen. And that's what happens. Traffic flows through your routers and your network. And that's going to occur based upon routing tables. So what routing tables are a map of the network to get from point A to point B. And we'll talk much more about some routing protocols, and we'll talk about much more about how these kind of things are going to work. And in order to make this work with routing tables, the routers need a map. So routers are like GPSs. They communicate to each other and they say, I have these addresses, I have these subnets, I have these subnets. Now they communicate to each other with things called the routing protocol. We will talk about one of the routing protocols used throughout this called BGP, but I just wanted you to understand the way networking works. It's basically hot potato. Pass something from router to router to router to router based upon the map that exists in the routing table. So now you know what routers do. So let's look over some of the basics of networking communication. We're going to cover the OSI model, and we're probably going to cover it twice. The reason we're going to cover it twice is we're going to do it once in the introductory section, and we're going to do it once again in the AWS networking section. And we're going to cover this twice for the following reasons. It's important. So why does anybody care about this OSI model? The reason people care about the OSI model is it's how communication occurs across the network. But more importantly, in terms of just communicating across the network, It's how we troubleshoot things. If you can't figure out what's going on, you can't troubleshoot or what to break. So troubleshooting this is important. So 7 layers of this model. Layer 1 of the physical layer is cabling. That's it, cabling. So it could be a copper wire, meaning, and what you're going to be sending on the wire is electrons in the form of bits. Or it could be a fiber optic cable, and what you're going to be sending is light or photons across the cable. So these are the kind of things that will work. So physical layer, layer 1. The next layer in networking is layer 2, or the data link layer. This is the physical card. So think of the Ethernet card on your computer as layer 2. And at layer 2, we're dealing with things like MAC addresses or frames, at least with regards to Ethernet. Layer 2, we're dealing with frames. Now, layer 3 of this protocol is, realistically speaking, where you're talking about the network layer. And what is the network layer? This is the logical layer. This is where we put our IP addresses. This is where we do most of our routing. The network layer is basically IP addresses. And the next layer we'll talk about is the transport layer. And this is where we're going to determine whether to use TCP, UDP, ICMP, or something like that. So we're going to cover the entire OSI model very shortly, but because we're just doing the intro to networking, we're going to cover the first 4 layers, which is really networking. Now, when we go into the AWS cloud a little bit in about 10 minutes, we'll cover it a little more depth, especially because we know people come in and come out. But for right now, since we're just talking about networking, we're only talking about the bottom 4 layers, which are the physical layer, wire, cable. We're sending bits over the wire. Layer 2, data link, Ethernet card, Ethernet card. And because it's an Ethernet card, it's going to be data link, and we're going to be dealing with MAC addresses. Layer 3, or network layer, IP addresses. Layer 4, or transport layer, you're determining the session, and you're going to be sending segments. So layer 1, bits. Layer 2, frames. Layer 3, packets. Layer 4, segments. So these are the things that are going to do. And I see there's some questions coming in. It's hard for me to do the questions and teach, but we were going to take a 10-minute break in about 10 minutes, and we'll answer any questions that are there. Chris from my team is aggregating them. So at this point, let's go start talking about the types of transport control protocols. And realistically speaking, we have 3 kinds that we're using predominantly. And it's going to be TCP, UDP, and ICMP. So TCP is the main protocol stack that we're talking about with regards to networking communications. So what is it by main protocol stack? So it's not just TCP IP. There's a suite of protocols that are involved in here. ARP is involved in here. There's an entire protocol stack. But at the transport layer, which is what we're going to talk about, there's really only 3 ways you would send your traffic, predominantly 2. We're really talking about TCP and UDP. So what are we talking about here when we're talking about sending data? We're talking about flow control. So if I wanted to send streaming video like we're doing right now, sending large amounts of data to people all over the world in real time. By doing this, I want to use UDP. So we're using some form of real-time streaming or UDP datagrams. And the reason we're using UDP is we're sending non-reliable transport with real live stream. What do I mean by this? If I send one of you data and we lose a couple of packets along the way, nothing happens. Maybe your video goes on not as perfect as it looks, but nothing bad happens. By comparison, we'll talk about that. So UDP, non-reliable transport, things like streaming media, things like audio, things like live video. Streaming media is super important. That's why we're going to use UDP. UDP real time. Here's what happens. If I send something to somebody on the other end and they don't receive it with UDP, I have no idea to know how. So that's why it's called non-reliable transport. Now, by comparison, if we use TCP or reliable transport, something different happens. Here's what's so different about what happens with TCP versus UDP. When we're dealing with TCP, we're using reliable transport. So, for example, at TCP, here's the way it works. Let's say Harry's on the call, and I send Harry a message, and Harry says, Mike, I got it. So then I send Harry 2 messages, and Harry says, Mike, I got it. So then I send Harry 3 messages, and Harry says, I got it. And I keep sending messages to Harry until Harry doesn't respond and say, I've got a message. Then I slow down and I restart transforming. So TCP, or Transmission Control Protocol, is used when you need reliable. What makes it reliable? It's the acknowledgement protocol. So by acknowledging that you've seen it, that you've sent it, that you've received it, we know that you've actually gotten access to the data. So UDP, real time. TCP reliable, and then there's this other layer 4 protocol called ICMP, or Internet Control Messaging Protocol. Let's say, for example, I want to see if a website exists, and I do ping www.amazon.com. I'm sending an ICMP echo message, which is, by the way, are you there? And I'm going to get an ICMP echo reply, which says I'm here. So let's go through it again. This is important. UDP, Uniform Data, is sent for non-reliable transport, real time, when you need things in real time. TCP, like if you're going to send a file or something important, send it via transmission control protocol because you need to know it got there. ICMP, network testing, and that's it. So let's get off of this topic. Let's get more into some more fun things. So let's define some of these network connections. We're going to define LANs and WANs in a little bit. So a LAN is a local area network. What do I mean by local? Inside your same building. Inside of your building, you've got a network. They're all plugged into each other via switches and high fiber connections that are short connections. That is a LAN, or a local area network. Think of your campus. Think of your data center. Or in AWS, think of an availability zone. Every data center that AWS has is a LAN. It's an example LAN, and it's an availability zone. So now you know what a LAN is, a local area network. LANs are high performance. Why? Because it's a cable, and you can push a lot of speed over a cable, and you're not paying that much for the cable. By comparison, a WAN, or a wide area network, is over a long distance. And because you're basically purchasing a wire or the equivalent of a wire from a service provider, WANs or wide area networks get expensive. Because you're paying for speed and distance, WANs are typically much slower than LANs, especially at cost. It could easily be, $100,000 a month for a WAN connection length at 100 gigabit per second over a distance. Whereas in a LAN link, 100 gigabit connection, by the time you're dealing with the cards and the cables locally, might be 5,000 one time forever. So WAN connection is much more expensive and slower as a rule. Now, we'll talk about cabling, but when it comes to cable versions, yes, it does matter a lot for LANs. For example, if we're going to be dealing with 100 gigabit, we need a type of cable versus different than 10 gigabit, which is different than 1 gigabit. Also, when it comes to LANs and it comes to cabling, there's a lot of idiosyncrasies based upon the distance that you're going, determines what kind of fiber. But LANs, local, high speed. WANs, long distance, you pay for them. Big expensive things, you've got to pay for someone else. So let's now look at what a LAN would look like conceptually. This is a pretty common LAN that you would see. Let's say you've got a campus, and in the campus you've got two buildings, and they're connected to each other with some fiber underground. Still LAN, local area network. You've got site 1 and you've got site 2. They're plugged into their switches and they're routed in between them. Conceptually, this is what a LAN looks like. Everybody is constrained in a small geographic area. That's your typical LAN. Now, when we're introducing the concept of LANs, or local area networks, we're also introducing a concept of a switch. And what a switch is, it's a device where people plug in. Now, by default, most people plug in their servers into a switch. And each switch, for example, and Joe will talk to you later, but a direct connect is a WAN, and we'll definitely get to all these things in lots of depth. But when people are plugging into a switch, they're plugging into a LAN. Now, out of the box, when you're dealing with a switch, we told you what routers do. Routers forward packets. Switch is where you plug your stuff in. So typically speaking, in a standard switch or an unmanaged switch, if you plug in every port in the switch is all in the same switch, meaning all in the same LAN, which means if I've got 100 ports in a switch and I do nothing with the switch, everybody in that entire switch could talk to each other. Right? No big deal. Makes sense to everybody, right? So, what if you wanted to make multiple LANs and you didn't want people talking to each other? You'd have to keep them separate. So, you would. So, let's look at virtualization of the network, which started 25 plus years ago, which, oh, by the way, is now how the cloud's built. And it's all coming from this virtualization concept, and it all started with the virtual LAN. Now let's look at what VLANs are, because it's part of our introduction to networking, and it's also going to be how you're going to connect to AWS. Let's do this real quick. Let's pretend, for an example, we have a switch, and it's got 500 ports in this switch. Now, big, high density, real expensive switch. We got it from Cisco or Juniper, great quality switch. 500 ports on all the line cards. If we plugged all the ports into each other, everybody would be able to communicate with each other, assuming they're on the same subnet. But what if we didn't want that? What if we wanted users in accounting to be separated from the finance people, which were separated from the developers, which were separated from a development and test environment like a lab? We could chop that switch into multiple logical switches. Looks like server virtualization, but 20 years prior to server virtualization, guess what it is? So about 25 years ago, when I first started with virtualization, what was actually going on was we would take a switch and we would we would chop the switch into logical switches by creating a virtual LAN. And all a virtual LAN is, let's say the switch has 100 ports. Let's say you put ports 0 through 24 in one LAN, VLAN, and ports 25 to 49 in another one, and 50 to 74 in another virtual LAN, and 75 to 99 in another virtual LAN. You would have 4 complete logically isolated switches in the same switch. How cool is that? One switch chopped into 4 switches. Hey, by the way, one server chopped into logical servers, virtualization. One operating system swapped into multiple containers, virtualization. All old technology. The cloud's old. It's just new because not everybody's been building it like me for 25 years. So virtual LANs, take a switch, chop it down into multiple logical LANs, now you've got a virtual LAN. So what if you've got multiple switches? Well, you've got a couple ways you could do this. So I want to show you how you could create communication between 2 switches. The reason we're going to go into this in this depth here is it's going to be particularly important later when we start talking about direct connections and how to get there. Let's say, for example, we had 2 switches and we created 4 VLANs in each switch. A VLAN A in each switch, a VLAN B in each switch, a VLAN C in each switch, and a VLAN D in each switch, just like we've done here. So, because we've got multiple switches and multiple VLANs, realistically speaking, they're logically isolated from each other. So if you've got 2 switches that are separated from each other and you wanted them to talk, you could run a cable directly from VLAN A to VLAN A. You could run a cable from VLAN B to VLAN B. You could run a cable from VLAN C to VLAN C. And you can run a cable from VLAN D to VLAN D. And guess what? Everybody's talking to everybody. This will work. This, by the way, would be the old way we used to do it. We would have switches and we'd run cables from VLAN to VLAN. Works perfectly. Here's the problem. What if you only have one cable? Well, now you got some challenge. So, what are we doing with VLANs? When we want to connect one switch to another switch, we've got to make it do something called the trunk port. And what is a trunk port? A trunk port is a port that enables you to put multiple VLANs on a single cable. Multiple VLANs on a single cable. So because you're putting multiple VLANs on a single cable, you got to segregate your traffic. So how does this stuff work? When you're segregating your traffic, what's going on is you're taking your packet or your frame and you're putting your frame into something else. You're encapsulating it. So when it leaves the first switch, it's wrapped in another frame called an 802.1q tag. And when the receiving switch receives it, it pulls the tag off and then places the data in its appropriate VLAN. So when you're dealing with multiple VLANs and multiple trunks, what you're actually doing is you're tagging a packet, or a frame I should say, and you're using it to put all the same things on the same wire, but keep them securely separated. So virtualization or VLANs is virtualizing a switch. 802.1q tagging is adding a tag so that when you send it across the trunk port or the single wire between 2 switches, you can share your information. So that's realistically the way these things are working. So now you know how VLANs work. Looked like there were questions with regards to software and hardware. On a good switch, VLANs are hardware. Now the configuration is done in software, but the work is done on FPGAs or ASICs. On good switches, all of this stuff is done in hardware. Software-based switches, not really. Unless we're talking about software-defined networking, which is another thing, which are basically these cheap commodity switches with powerful CPUs that are doing things in software. But good switches do all the stuff in hardware, all the big core important stuff. Now, I initially talked a little bit about what wide area networks look like. Conceptually, this is realistically speaking what it actually looks like. Basically, you've got a customer, you've got an environment where you purchase from a service provider or a telco a wire from point A to point B, and then you connect across the link. So that's kind of the way these sort of things work, where you basically have a wire that you're purchasing that you're purchasing through the phone provider switches and things, and it's transparent to you. Now, it used to be that we used serial interfaces like T1, T3, and then we were using ATM and then optical interfaces. For the most part, everything's Ethernet. My team at Riverstone, we were working very heavily 20 years ago on layer 2 tunneling Ethernet frames over an IP network, and that's what we're doing now. So in today's world, we're typically dealing with pseudo wires. And what are pseudo wires? It's basically the service providers giving you a wire over their network. Now, in this particular example that I showed you, what we're talking about is we're using a standard WAN, where basically you would buy a fiber optic connection to your service provider's local point of presence on both sides of your link, and then you would ride across the service provider's WAN service. So basically, you're just buying a wire. Now, in a more modern kind of environment, we're dealing with Ethernet over MPLS. And what Ethernet over MPLS really is we're just tunneling IP traffic over an MPLS network. So when I told you when we were doing VLANs, where we basically took our frame and we encapsulated it in another frame, in an Ethernet over MPLS environment, we're doing the same thing. We're taking our frames, we're encapsulating in another frame, and that's how things go. So that's all Ethernet over MPLS is. Now, 2 more things on IP, then we'll take a break, we'll answer any questions, then we're going to get a little bit into AWS, and that's when the fun begins. But we've got to start with the baseline for somewhere. So let's go back to that routing example I gave you in the beginning, and let's look at it. Let's say PC1 wants to send something to PC2. What does PC1 do? PC1 says, how do I get to PC2? PC1 says, do I have a route in my routing table? And if PC1 says it has a route in a routing table, it would go there. If PC1 doesn't have a route in its routing table, it's going to look for the route in its routing table that most closely matches it, which most PCs have a default gateway. And if you're not sure, and you're on a Unix machine, do something like an ifconfig. And if you're on a Windows machine, go to the command prompt and type ipconfig/all, and you will find your default gateway. And your default gateway is the router where you send your traffic for which you don't have a destination. So if PC1 wants to go to PC2, it's going to see if it has a route. If it doesn't, it'll use its default route. When it gets to router 1, it's going to say, do I have a route in the routing table to PC2 subnet? And it's going to look, and if it doesn't, it'll drop it. If it does, it's going to say, wow, I have a route. It's through router 2. It'll send it to router 2, and once it gets to router 2 will say, I have a route to this. And because I have a route to this, because it's directly connected, I know that it's connected to me, I will send an ARP broadcast. ARP, who has the MAC address for PC2? PC2 will respond with its IP address and its MAC address, and it will send it back and forth, and that's how much the communication works back and forth. So that's how routing works. Now, one last piece of housekeeping to cover the introductory section is what's going on in the header. What's going on in the header is as follows. Every packet has a header. Now, what's going on in this packet header is going to be really important. Why is me, a practical guy, an architect, covering all this basic fundamental header stuff? Because the stuff in that header is going to be really important when we start talking about packet filtering and access lists and quality of service and important things. That's why we're doing it. So, the header, which is a part of the packet, which basically tells the packet where it should send its data, is as follows. It first gives you the destination address. That's where your data is going. That's how you know. How do you think the access control list looks at your router? It's looking for the destination IP address. It also tells you the source address. The source address is your address who started the sourcing the data. Again, an access control list can look at your source address. If you've got an attacker attacking your system, block their source address, they can't get in. The next things that are in the packet header are as following. The time to live. What is the time to live? Every time a packet goes through a router, it has something called the TTL, which is degraded. The time to live is how many packets a router, how many routers the packet can go through before it times out. See, if we had packets and they didn't have a time to live, and there was no route to the destination, the packets might be floating around forever until they got lost. Or if you had a routing loop, packets might be going around forever and filling up your network. So the time to live, it basically means that if you can't deliver your traffic in a reasonable period of time, like a real reasonable period, but your traffic gets dropped. And it can be as high as 255 hops. It can be a large number. Now the protocol is TCP, UDP, ICMP, just like we talked about. Now let's just header check something. The header checksum is basically something that will tell you, it's a mathematical calculation that will tell you if the packet got there okay. Meaning, did the data get there right? So that's what the header is. So you can see the destination and source addresses, the TTL, the protocol, and then the packet length. What is the packet length? How long it is, how many bytes, like 1500 bytes, for example. And then the last things that we'll talk about is the version, is the TCP version. And then we'll talk about this DS field. So what is this DS field, or the degree of service? The degree of service field tells you how important the data is. So if you want to use your application to prioritize data, or you want to use your network to mark this data as prioritized, you can then set up a queuing policy that says Mike's data goes before Ned's data, who goes before Nick's data, who goes before Deep's data, or vice versa, or any policy you want. That's what this DS field is. So we've been talking for approximately 20 minutes. Actually, looks like my camera's doing something pretty funny, so I'm going to go mute the camera and so it cleared itself up. Don't know what happened there, so we cleaned that up a little bit. So let's open it up for any questions for a few minutes. Who has some questions for me? So we talked about it does matter which cable version you use for the LAN. The next question is SD-WAN. We're not going to talk too much about SD-WAN in here because SD-WAN is a completely separate topic. But if you guys like, perhaps we'll do an SD-WAN training session coming in the next month or so. Pretty big topic, but something we can happily talk about. Joe White, is direct connection a WAN? Yes, Joe, a direct connection is absolutely a WAN. And when we talk about it, we will show you all the module components, and a direct connection is a WAN. Because a direct connection is a WAN, Joe, and that is a really great question, it adds a lot of latency. So as a cloud architect, you're going to have to look at the applications and say, can the application actually tolerate the latency of the WAN? In 98% of the use cases, the answer is yes, but in 2% the answer is probably no, because it's a WAN. So when you're designing your architectures, whether they be multi-cloud or hybrid cloud or all in the data center or a combination thereof, you got to look at that. And because it's a WAN, you've got to think about that. We answered Shakula's question. VLANs are typically done at the hardware level, where you configure them as software, but all this forwarding and all these really good routers and switches, at least the high performance ones, are all done in hardware. And Deep, the difference between a router and a modem, well, here's what a modem really does. A modem is a means to take a digital signal and send it over an analog line. It used to be a dial-up modem, which we used, and basically these things would connect and they go doo 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 doo, and then by tones they would actually send our data. That was a modem because we were trying to send digital data over an analog line. Then we started using DSL, and basically we were using modem to send digital data over an analog copper wire. And then we're still using modems with cable because cable is not really designed to do digital. So when we're using a modem, it's to translate digital to analog, over a digital signal over an analog line. A router, by comparison, is a computer with lots of interfaces. Pretend I have like 20 different arms and they're all going in different directions. And a router builds a map and says, to reach destination 1, go this way. To reach destination 2, go this way. To reach destination 3, go this way. To reach destination 4, they go this way. So that's what a router does. A router builds a map of the network, uses an algorithm to determine how to get to the best locations, and a router does that. Now, in certain home user environments, no, this isn't really networking, this is basically home stuff. You can get like a fiber optic connection to the home. They give you a modem and it's got a router and Wi-Fi in there, but that's combining it. But when we're talking about switches and we're talking about routers and we're talking about architecture, we are talking about these big $100,000 plus devices that have redundant power supplies, redundant modems, all kinds of incredible things. So now you kind of get a good example of what's actually going on in these environments. So let me go through before we go to the next topic. Does anybody have any more questions? Because if you've got any more questions, let me know. And the reason it may look like I'm sitting here waiting for you guys to ask any questions is because there's a 30-second delay. William Wallace, is the IP header what you would use for WAF or any firewall? Yes. These firewalls are looking at the IP headers to actually determine source destination, type of service, and everything. What Raphael was alluding to, which is something I didn't really talk about, here's what goes on. Realistically speaking, you can only put a certain number of hosts in a subnet. And what's going on here is all these hosts, every computer, they do these broadcasts. One of them is ARP, who has this, who has this, who has this. Then you've got these NetBEUI, NetBIOS, all these other weird window and Apple things where they're like, I'm here, I'm here, I'm here. And all these devices are broadcasting, screaming, full of information to let everybody know that it exists. And once you get above about 250 devices in a network, they're all screaming, I'm here, I'm here, I'm here. You get a lot of broadcast traffic on your network. Broadcast traffic is something that one person says that everybody has to receive, whether they want to receive it or not. So it's going on. This broadcast traffic is coming in. It's going on. Broadcast. Every host in the system is looking at it, is looking at these things, and they go, I process it. And the problem of processing all these things, after you process all the data, it hits the CPU. So broadcast traffic affects your routers, your switches, and your servers. So what you do is by creating subnets and routing between them, you limit broadcast domains, and that's why people are using routers. So it used to be, and then I'll talk about if you guys want a broadcast domain versus a collision domain. So realistically what's going on, 25, 30 years ago, we have something called a hub. Nobody's used a hub in 25 years. They were a horrible idea. What happened is everybody would plug into the hub, and when they were all plugging into the hub, what would happen is they used these things. By the way, Wi-Fi uses this. It was called CSMA-CD. And basically what happens if you had 10 people in a hub, and I tried to transfer and somebody else was trying to transfer, we both couldn't send our data at the same time. Our data would collide, we'd both stop sending. And then we would randomly back off, and it would be like, oh, maybe I'll try, and then maybe somebody else will try. And we'd both be trying to send data, and poof, our data would collide and we'd restart again. So it used to be that these hub things were a broadcast domain, and by using a collision domain. So we got rid of hubs 25 years ago and replaced them with switches. When we went to switches, the concept of collisions completely went away because every port is in its own collision domain, and the only thing that got left over was a broadcast domain. Everybody in a VLAN can see each other's broadcast, and that's it. Unless you do other things, but that's to constrain that. But that's realistically what's going on. So how much of the cloud and networks are adopting IPv6? Well, IPv6 is the majority of things what we're using right now, but IPv6 is largely used by every mobile phone has an IPv6 address, and new networks are adopting IPv6 slowly, but almost all IP phones are there. William Wallace, with SQS, it has nothing to do with the router at all. Routers have their own queuing systems for data. SQS is an AWS thing that was designed more for our servers and things, totally unrelated. Rob Deutner, where does the autonomous system come into play? That is only used with regards to BGP routing. We will have lots of fun with BGP throughout this program. I know it's not completely covered in the AWS Advanced Networking, but it's expected you need how to use it. In networking and cloud, you're going to be using BGP everywhere. So we will include a pretty good amount of knowledge in terms of how to do BGP, way above this. We're not going to be like a certification program that says, read this BGP book, but we're not teaching it to you. We are going to teach you the basics of BGP and how to tune it and how to optimize it and how to perform it, because we want you guys to be fantastic cloud architects. Okay, it looks like we're ready to go to the next section. Let's start talking about the AWS cloud and how it's organized. Now again, some of this may be refreshing the content, and some of it may be new depending upon your background, but we want to make sure that everybody's good all the time. So let's go talk about how the cloud and how it's organized. Now, one more question. The last question was, does AWS have their own IPS system? They do, but if you're really designing a high performance, high availability system, you're going to be using something that comes from the marketplace. And we're not going to be using WAF. We're going to be using something much stronger than that for enterprise clients that matter. So we can teach you how to do that when we get to these sections. WAF is fine, but if organizations need real security and real IPS systems, they're going to be doing much more sophisticated things than WAF and Shield. And we'll talk about how that works throughout the program. Like I said, we're teaching you how to be architects, not just pass a certification exam. So let's talk a little bit about the cloud and how it's going to be organized. The cloud is going to be broken down into multiple sections, and most of you know most of these, but we're going to cover the other ones in case. We're going to talk about regions, we're going to talk about availability zones, we're going to talk about local zones, and then we're going to talk about edge locations. Now, think of it this way. A region is an incredibly large geographical area. Think like a continent or part of a continent. An availability zone is nothing more than a data center inside of that region. We're going to talk and show you more about local zones, but local zones are really an extension of a region. Remember, I told you that you're using a WAN connection to connect to the service provider. WAN connections have latency. Latency is the enemy of some applications. So if you've got a real-time application or a latency-sensitive application, you need to basically do something that has less latency. And that's what the local zone's for, by getting it closer to the user. And then we'll talk about edge locations. So let's walk through, visually speaking, what some of these things are. Let's look at the cloud. So AWS Cloud, large geographic region. And inside of them, data centers called availability zones. No big deal. Region, US, or East Coast US, or what have you. Data centers, availability zones. Now let's talk about a local zone. Now the local zone is kind of more on this networking thing. The local zone is pretty important. The local zone is getting kind of cool. So what is the local zone? The local zone is a place where you can run your latency sensitive applications closer to you. So what is it really? Think of it as a data center that's closer to you than the AWS availability zone and region. So just extending the region. So you're going to have the opportunity to have computing power closer to where you're actually at. And by doing this, you don't have less latency. Reduced latency, improved application performance. Wonderful, wonderful, wonderful things. So that's what we're talking about with local zone. Now, in order to use these local zones, and I'll show you visually what they do, they're not enabled by default. In fact, you're going to have to opt into them. And that is fine. It's great. Opt into them. Local zones are terrific. Lower latency, better performance. The cloud's starting to feel almost like the network in the data center. Remember, the cloud's just a virtualized network in the data center with much lower performance. When you start adding things like local zones, the cloud starts to perform a lot closer to the real-life environment, which is really fantastic. So we're excited by local zones. What happens is you opt into the local zones. You're going to create a subnet to use them. And in these local zones, you place your EC2 instances, your load balancers, your containers. And if you're lucky enough to be one of these local zones like LA, for example, you can put in a file system for Windows, Elastic MapReduce, Elasticache, RDS systems, and even dedicated hosts. So some of these environments are going to get pretty great. So let's look about visually how you're going to use them, what you're going to use them. So if you want to use these local zone edge computing, first you enable them, then you extend your VPC into the local zone, and then you're going to build and run your low latency applications, and that's how it's going to work. So let's look at it from another perspective. Here's your region. And inside of your region, you're going to have your availability zones. But this local zone, think of it as, let's say there's a local zone in Miami, and I'm in Palm Beach over here. Instead of me having to send my traffic all the way to Ohio to the closest availability zone, I could just send it to Miami, which is like 60 miles away, which is going to give me fantastic latency and performance. The last thing that we'll talk about are actually edge locations. And when we're talking about edge locations, what we're really talking about is CloudFront. CloudFront. So CloudFront, which we'll talk about much later, which is a content delivery network, is really a place where we provide local access to the cache for CloudFront. And we'll talk about it. So the edge locations are where CloudFront is. And I'm going to show you exactly what that means. But basically speaking, there's a CloudFront edge location in almost every city. So architecturally looking at it this way, you've got your availability zones inside of your regions, and you've got these edge locations. So these edge locations are typically speaking what you call point of presences. And what a point of presence is, it's a place where you've got large numbers of internet service providers, lots and lots and lots of them, and they're all in the same building. Why would you put so many internet service providers in the same building? Well, they can just run a cable between their routers and then they can all talk to each other. So if you need a lot of network bandwidth and your top 10 ISPs are in the same room and you want to put multiple 100 gig links between them, real simple, just a simple cable cross connect, high speed, high performance. And by setting it up in this way, if I'm on AT&T and I need to jump off AT&T's network to the Verizon network, we're in the same building. It's these point of presence with our BGP peering locations. So that's what edge locations were always in networking. But edge locations are here or really in the concepts of users accessing their data. And here's how it's going to work. And we're going to cover content delivery networks and CloudFront in much, much, much more depth coming soon. Trust me, I promise. But until we get there, the way it's going to work is if a user wants to request a web page, the user is going to go straight to their edge location. And if the information is cached in the edge location, it's going to be sent back to the user. But if it's not, and the user goes to the edge location and the edge location doesn't have it, it'll send it then to the regional cache. And if the regional cache doesn't have it, it'll send it to the web server. And then it'll send back to the web location, the edge location, and then it'll send it back to the user. Now, the next time a user tries to access the same thing, they'll hit that same edge location, and it'll be, the data's already there because somebody requested it. It'll get sent straight to the user. So that's what edge locations are. So now we're going to start talking about some basic networking concepts. But before we do that, let's just make sure nobody has any questions on the edge locations, local zones, or other places. So if anybody has some questions, great. Otherwise, if you enjoy networking, please type networking. And if you want more training like this, more free training, type Cloud Architect. Some way that we know that you're there and we can listen to what you're hearing and we know what you want. We want to give you guys as much training as we possibly can to help you guys out for your careers. My team has also asked me to ask you all to like and subscribe if that's appropriate for you. So I've been asked to do it, so I'm asking the question. So please like, subscribe, and hit the bell. And yes, edge locations are part of the content delivery network. The true content delivery network we'll talk about that in a minute, but edge locations are part of the content delivery network, but not the entire content delivery network. Eric, I am so happy to see you on this call, on this session. You have no idea, Eric, so thank you for being here. I'm thrilled and thankful that you're able to be here today. I know you've been very busy in your life. So the question came through, is a local zone the same as a data center? The local zone is like a data center at the edge of the network. So yes, it's going to be a data center, actually. Great question, Anurag. Let's see, I want to make sure there's no more questions before we move on. What is an edge location? Okay, an edge location is, I will give you as follows. And then I'll give you an answer for those next questions. So an edge location is where a user would access CloudFront. So a user comes, they hit the CloudFront edge location. The CloudFront edge location is basically a point of presence or a little mini data center in every city where your things are, which then gets forwarded to a regional cache, which then goes to an availability zone. So an edge location is where users access the CloudFront content delivery network. A content delivery network is not just an edge location. A content delivery network is a network. So with regards to the internet, all traffic on the internet is what's called best effort delivery. If I buy a private line from New York to London at 1 gigabit, I know that when I'm buying a gigabit Ethernet, I'm going to get 1 gigabit. The latency will never change because it's a wire. It will never change because it's a wire. And that's what's realistically speaking what's going on. The latency won't change. By comparison, if it's the internet, as soon as I buy traffic to the internet, there's no guarantee of the performance of my traffic. None. Zero, zero, zero. Because there's no guarantees of my traffic, then the internet performance cannot be guaranteed. So what goes on is organizations build high-performance content delivery networks. And what is that? Let's assume that you didn't want to use the internet. If I wanted to use the internet and I wanted to go straight onto the edge location, if it exists in the edge location, it's cached, it's going to send it to me. But if not, from the edge location is going to take me across the content delivery network's private backbone. So it would ride the AWS backbone instead of CloudFront as opposed to internet. So once I jump on the content delivery network, I'm off of the internet. So I hit my edge location, which for me is in Miami. Instantly, I ride the AWS high-speed backbone back to AWS. So the content delivery network not only does caching, it gets my traffic off of the public internet and onto the private network, which really enhances speed, performance, and everything else. Hope I answered your question. So EC2 instances exist in local zones, not edge locations. Next question is a local area network part of a specific AZ? A local area network is anything that is local, meaning it's typically in your data center. If your devices are all inside of an availability zone and you can guarantee that they're part of that availability zone, that is inside of a local area network, yes. If you're going across availability zones, if they're in the same part if they're in the same what do you call it? If they're in the same building where it's just a fiber optic connection, it's again like buildings across the street, local area network. If the availability zones are separated by 500 miles, it is not a local network, then it becomes a wide area network. Okay, if you make a change to a website hosted on your content delivery network, how long will how long will it take to propagate to your content delivery network? It's based upon the TTL of your caching. If you have a TTL of 24 hours, it'll take 24 hours for new data to be moved over. If your TTL is 1 minute, it'll be over in a minute. So that's with regards to that. EC2 instances reside in local zones, not edge locations. How do you start learning as a network professional? Well, there's two ways to do that. I've been a networking professional forever. The first and best answer I can actually give you is we have created a complete cloud architect career development program, and it's a 16-week program, and it's designed to take people regardless of their background and teach them how to become cloud architects. We start at the beginning. We cover every component of the network, every component of the data center, every component of the servers, virtualization, firewall, switches, security, everything. Then we cover all the applications that are used in these environments, how to build them and how to design them. We spend 3 hours twice per week with our students designing live cloud architectures. We do it every week. We do it on Mondays and Fridays. We do 6 hours of live training in between classes, personal. We have videos on demand, and what we do in between sessions is we have our students build and do labs. And when our students do labs, they do things that matter. They learn server virtualization, they learn containers, they build firewalls, VPN devices, all the such. In addition to doing all these kind of things, they set up Linux, Apache, MySQL, PHP, pstack, literally everything. They set up file shares in Linux and Windows. They set up Microsoft Active Directory. They learn every piece of the network in the data center. You can't design a cloud architecture if you don't know the data center, because the cloud's just a data center, just virtualized. And then we even have our students build their own clouds. I'm not joking. Our students build their own cloud computing environments from scratch. Because when it comes to getting your first cloud architect job, you need to be good, you need to be solid, and you need to be super competent when you lack experience. So we do that. We also teach presentation skills, writing skills, emotional intelligence, interview skills. It's all included in our training program. I'll drop a link of our training program. Because you asked over here. And then actually better yet, so this is a link to our training program. I'll drop a coupon code and then I'll go back to answering questions. And if other people are curious about our training or want to know how to do things, they can always call our office. And we're always happy to work with new students. People call us, we work with you. So that's how you would move into this. Now the last question is regarding transfer acceleration. None of this has anything to do with transfer acceleration. Transfer acceleration is actually used when you're dealing with files that are uploaded to S3. It's basically, but that's neither here nor there. But it does use something similar to this where you're jumping on to a closer location to do it. Very similar concept, but it's different. Everybody's ready to get back to it. Let's start talking about some AWS networking. So now we're going to get into some AWS networking concepts. And in this section, we're going to cover a lot. We're going to cover the cloud, which means, and then we're going to cover the VPC. And when we start covering the VPC, we're going to cover a lot, everything from IP addressing to you name it, it's all part of the VPC. So we're going to begin. So what is the cloud? First and foremost, the cloud is nothing more than a virtualized network in a data center. It's going to have your LAN and your WAN fully integrated. It's going to have your servers. It's going to have your storage. It's going to have your security. It's going to have all your DNS, all your load balancers. So the virtual private cloud, people like to call it a virtual private network, but I like to view it as a virtual private data center because it includes your network and your data center. So, and it's going to be logically isolated. So whatever you have in your data center, it's going to be isolated and separate from all the other AWS customers. Remember how I told you when you create a virtual LAN where your things are logically separated from everybody else? Well, same thing. Your things are kept separate. And that's what's going on. Our traditional network engineers like us going out, we have to migrate to the cloud because the cloud has basically made everything so simple. that we need to be there. Lots of jobs for cloud architects in the network engineering space. So much of it there. But we need to migrate towards the cloud, and that's why we're doing that. And yes, we do help people with resumes as well as introducing them to recruiters as part of our program. Going back to the cloud, I want to go talk about it one more time. I'm going to go back to this OSI model. And I know I talked about it before. I only went from layer 1 to layer 4. So we're going to do it real fast here because we know people aren't always necessarily here for the entire session and they come back in. Real quick, layer 1, the physical layer, it's the wire, the cable, fiber optic or copper or otherwise. Layer 2, data link, hardware, and MAC address. Layer 3, IP addressing and routing. Layer 4, transport layer, TCP, UDP. Layer 5 is session, basically controls the connection. And layer 6 is presentation. What goes on at layer 6? Encryption. And what goes on at layer 7? That's the stuff you use. That's the applications. You say it once. Layer 1, you're pushing bits and bytes. And that's physical containers. It's going to be electrons or photons based on what's going on the wire. Layer 2, data link. That's the MAC address of your Ethernet card. We're sending frames. Layer 3, IP addressing and routing. Packets, IP packets. Layer 3, logical addresses. Layer 4, the transport layer, protocol, TCP, UDP, ICMP. Layer 5 or session controls what's going on at layer 4. And we're talking about sockets here. Layer 6, think presentation layer, think encryption. Layer 7, this is what you use. So when you go to Google Chrome, that's a layer 7 application. That's an application. So let's go back and talk about, when you would start addressing your things. So when we start looking in these environments, what is an IP address? Since I keep talking about layer 3 IP addresses, I want to make sure everybody gets its foundation strong and solid. An IP address is just a logical address that identifies a computer on a system. Every system, with the exception of when we talk about Anycast, and we'll talk about Anycast, must have a unique address. Just like the mail. Imagine if I wanted to send mail to you, and you didn't have a unique address. Your mail might go to everybody else that has the same address. Same thing here. If you don't have a unique address, how will the network identify you? It won't. So every computer has to have a unique IP address. And they can be real similar, but in the end they're going to be a little different. So just like you can have the same address, but you have a different postal code or zip code, same thing goes on with IP addresses and subnetting and the such. So for the internet to work, every device that has to talk to any other device must have a unique IP address. And we'll talk about workarounds for this and all kinds of things. Now we're talking about IP addressing. We're talking about two versions, IPv4 and IPv6. Now when we're dealing with IPv4, or the original addresses, we're dealing with a 32-bit address, which is the most common address. We're dealing with IPv6. We're dealing with the newer form address, and we'll talk a lot more about both of those kinds of addresses. So when I began, there was no IPv6. We were all using IPv4. And IPv4 was perfect, but it's a 32-bit address, which gave us a whole lot of addresses, but no one really thought the internet was going to go anywhere. The internet was this experimental military university thing that was small, real small. And organizations were given things like a Class A address with 60 million addresses just for one system. And, these kind of things kind of existed. But, now that's not the case anymore. So now what's realistically speaking, what's going on is where you're going to be migrating to IPv6. But let's go back to this IPv4 because most of the addresses were still going to be used. Because we ran out of internet addresses so fast, and we were going to, the Internet Engineering Task Force came up with an RFC 1918 which specified private IP addresses. What were these private IP addresses? These were IP addresses to be used internal to your organization. So what would happen is organizations internally will be using these private IP addresses, and then externally you're going to be using public IP addresses, which is fine. So that way, internally organizations didn't have to waste IP addresses. What a great idea. So what happened is all these organizations used these private RFC 1918 addresses internally, and when they had to connect externally, they would use public addresses. This worked great, and it's helped save us for years. Remember, private IP addresses are used internally. They are not globally routable. They are not unique. used inside of your network, but not outside of your network. So then we had something crazy called IP classes. And this was another silly thing to think about. We used to have this concept of a class A address, which basically was a /8, and then we had a class B address, which was basically a /16, and then there was this concept of this class C address, which was basically a /24, and then class D addresses are used for IP multicast, and they're still used, and then class E is reserved. So what ultimately happened was, if somebody was given a class A address, like 1.1.1.1, with a subnet mask of 255.0.0.0. Sorry, I don't necessarily make all my own slides. I have some people that help me with the slides. Actually, no, never mind. I can see what they did here. That was my reading it wrong. So wonderful to hear this, Joshua. So the Class A addresses would give you 16 million potential hosts. But if you put that Class A address on an Ethernet interface, that was it. They were all used up. Because every subnet, like if you have a server with 2 subnets, the server needs 2 interfaces, and they each need to be on a different subnet. So if you use the /8, which is 16 million addresses, on a single subnet, poof, it was gone. It was 100% wasted. So obviously you can't waste 16 million addresses on a single subnet. The next thing to do was the class B address. And a class B address was a /16, which gives you about 65,000 possible IP addresses. And again, if you would stick that on an interface, you'd be wasting 65,000 addresses. Now, from a practical perspective, you're never going to get more than about 250 addresses in a subnet because of broadcast, so just look at it that way. Next on the list came these Class C addresses, and we use Class Cs all the time, although there are other addresses basically subnetted down to a Class C. And a Class C was a /24, and they would give you basically 253 hosts per subnet, perfectly good, perfect environment, and Class D we still use for multicast. So all this would be great, but obviously that didn't work. So in today's world, what's really going on is we're dealing with classless addresses. What do classless addresses mean? Classless addresses means we're just not sticking to the silly little classful boundaries, the /8, /16, /24. It means we can subnet. And what subnetting does is enables you to take one network and break it down into smaller networks, or smaller networks and bring it into bigger networks. So thank you so much, Cool Dude 5699. Really appreciate it. So that's the way these kind of things work. So let's go work on what's going on. So what's going on is all these subnets are going to be, all these networks are going to be broken down into subnets. The routers are going to be exchanging information. Hi, I'm here. Hi, I'm here. These are the links that I know about. These are links that you know about. These are links you know about. They're going to build a map. And that's how they're going to get your training from point A to point B. That's how we're going to get it there, by building a map. That's what routing protocols do. So with AWS, they use classless interdomain routing called CIDR. Now you know what the CIDR stuff is. That's it. Customers are given a block, and you have to subnet that block for your IP addresses. That's pretty much it. So what is subnetting? Subnetting is a way where you take one network and you chop it down into middle networks by borrowing host bits and subnet bits. So let's look at subnetting in action. Let's look at this particular example. Let's say I've got this Class C IP address, 192.168.1.0/24. Perfect. Great. Now, let's say that's the only subnet I have in my CIDR range. What if I have 3 interfaces? I've got a problem. Why do I have a problem? Because I can only use one IP subnet per interface. So, what's going on here? In this particular use environment, I took the 192.168.1.0 subnet and I further subnet it down, or mathematically reduced it to the 192.168.1.0/28, which will then give me the 192.168.1.16/28, and then I'll have the 192.168.1.32/28, and then I'll have the 192.168.1.48/28 all the way up. So I took my network and I broke it down. Now by breaking your network into smaller networks, you're going to support less hosts, and that's okay. So you have to understand that as well. So here's where it gets kind of interesting, and here's where it gets iffy, and this is where network engineers like me, we got to look at it because it's a little on the ugly side. So typically speaking, you lose 2 hosts per subnet. And what's going on here, if you wanted to calculate the number of subnets per host, You have two options. You can do 256 minus your subnet mask, so 256 minus 240 equals 16. Subtract 2, the first address, the last address, and you would find out that you'd have 14 available hosts. That works. Alternatively, you could do 2 to the power of the number of subnet bits, which you've used, which in this case is 4. 2 to the 4th is 16 minus 2, and again you would figure out that you have 14 available hosts. In real life. But in AWS, you're only going to have 11. Now this is really important. Remember this. Test question, test question, test question. You run into any kind of subnetting problems in AWS, it's because of this. Remember this. Remind you in your head, AWS reserves the first 4 addresses and the last address. So not just the first one, which is the subnet, and the last one, which is the broadcast. They reserve the first 4 and the last one. And by doing that, they take away 5 addresses. Which means a /28, you only have 11 available addresses in AWS. You have 14 anywhere else, but only 11 in AWS or some of these cloud providers. Which means if you've used the subnet that's a /28, and you've got basically 8 or 9 servers and a couple of load balancers, and they go to attempt autoscaling, and they don't have enough IP addresses because you run out, you won't be able to scale up. They won't autoscale. So understand that if autoscaling stops, it's because you probably ran out of enough emails. So understand that completely. So normally, 2 to the whatever power minus 2, but with AWS, you lose 5 addresses. So we talked about subnetting, which, and I didn't mean to do that. We talked about subnetting, which is basically taking a subnet and breaking it down into little networks. Now, what if we have a bunch of little networks and we want to turn it into a big network? Well, why would we do that? Maybe we thought we only needed 10 servers in a subnet and realized we needed more. Well, we can expand the size of the subnet. Or more realistically, when do we really do it? Routing. We create something called supernets, which is route summarization. I'm going to show you what's going on. For those of you that were here in the beginning, or actually no, for the people that were on my training session this morning, and we talked about connecting to the internet with 10 different internet service providers and running BGP and pulling in 750,000 routes in from each service provider to determine the best path to a destination. Something's different here. AWS only allows 100 routes. That's it, 100 routes. It's nothing, literally nothing. Typical enterprise with 20,000 remote locations might have 50,000 routes on their routing table. Now you're with AWS and you've only got 100. Uh-oh, what are you going to do? Well, you're going to have to be really careful with your IP routing, and you're going to be really smart with your IP addressing, and you're going to have to come up with an address block that you can summarize and share this summary to the rest of the world. That's what you're going to be doing here. Route summarization. So supernetting is designed for route summarization, so you can send one route which promotes reachability. Now this topic is important, and when we deal with BGP and load sharing and traffic engineering, which is really important, this really matters. So if anybody's lost here, I want you to all ask questions because I don't want anybody lost here. So look what we've done here. We've taken the address, or the subnet, 192.168.0.0/24, 1.0, 2.0, and 3.0. Now we can aggregate or supernet or route summarize that into 192.168.0.0/22. See, when we do this, and we're subnetting it this way, what's going on is we're only sending one route. So if you only have 100 routes with AWS, look how awesome this is, only a single route. And that's how you're going to work around the AWS routing limitations. You're going to supernet. Supernetting is just taking multiple subnets and supernetting it, and you send one route. We will have a lot of fun with traffic engineering here, and it's going to be really, really, really fun. My team has sent me a message asking me to ask everyone to like, comment, and subscribe. If you're having fun, let us know. If you're enjoying it, like it, and that signals algorithms and all kinds of things to be happy. So let's just talk a little bit about IPv6. We're discussing IPv6. It's a newer form of IP address. Now I want to put this in the context. IPv4 is a 32-bit binary address. Do you know what binary means? 0 and 1. That's it. So if you want to figure out exactly how many IP addresses we have, our number of IP addresses that are available with IPv2 is 2 to the 32nd minus 2. You want to know how many in IPv6? It's a 128-bit hexadecimal address. Hexadecimal means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, all the way to 15. So, hexadecimal, 8 times the number of addresses, times 128 versus 32. I mean, exponentially to 38. So huge, huge difference. So now we talked about some IP addresses. We talked about some AWS things. Now we're going to get to the VPC stuff and all the cool stuff that's really in the heavy duty cloud routing stuff. Before we do, anybody have any questions? So now the question for Knowledge Drive before we do there. We provide completely free certification training for the Certified Solution Architect Associate, the Certified Solution Architect Professional, and the AWS Advanced Networking. We have free books for the Certified Solution Architect Associate. They're listed in the description below. And we have the Professional. Now, Knowledge Drive, I will tell you this. Certification alone is not enough to get hired. You must understand how all the systems work, how to design them, how to communicate them. Certification alone is not enough. But we do provide free certification for all of the major certification things. And if you guys would like us to do more free boot camps of things, let us know. Say boot camp or something below, and we'll try and find something to do each month to boost your careers. I'll never be able to do for free what we can do with our internal students, but if you guys are interested in us doing more boot camps, type boot camps below, and we will try and make a point of doing a boot camp of the month. So let us know. So Shakula, a /16 basically gives you 65. How can you break that down into multiple subnets? Our team will send you a video on how to do that, because there's never a chance that you're actually ever going to be able to work in architecture without understanding subnetting. You have access to us, Shakula, so our team will send you a good video on that. That video, we kind of assume that people at least have that basic kind of knowledge in order to do this, but we can definitely, I'll send you something for that since you're definitely part of our team. So anytime you're on a certain subnet where you borrowed a certain number of host bits, then the answer is yes. For example, it'll be subnet specific. So how does AWS take 5 me's from the subnet? Here's what they do. The first one is normally reserved for the subnet, and then they reverse the next 3 for Amazon only purposes. And then the broadcast address is reserved. So Amazon just chooses to reserve some extra ones. Can I show the slide for the SuperNet again? Absolutely. So really what's going on here is we've got 192.168.0.0, and then 192.168.1.0, and then 192.168.2.0, and then we've got 192.168.3.0. So you're all with me there, right? So if we were to borrow some hosts, so let's say we did 192.168.0.0 and 0.1. We could supernet that in terms of a /23. We could also supernet 192.168.2.0 and 192.168.3.0 as a 192.168.0.0. I'm sorry, as a 192.168.2.0/23. Now we can aggregate all of these in terms of a /24. Now what if we wanted to go 192.168.0.0 all the way through 192.168.7.0? What do you think the subnet mask would be there instead of /22? We'd borrow an additional subnet bit in order to do that. So what would that change the subnet to, everybody? A /2 what? If we want to include the 192.168.0.0 all the way to 0.7, or to .7, if we want to go 192.168.0.0/24, all the way to 192.168.7.0/24, what would that subnet be? They would aggregate all of these things. /21, exactly, Nick. Knowledge Drive, a boot camp is like this, where we do teaching every day for a couple days to try and provide some free training education. Srinavis, great job. Yes, this is a boot camp. This is day 1 of 4, Alexandra. And somebody asked earlier about transcripts. I'm assuming, I think YouTube automatically enables a transcript for this after it's been done, so it should be there. Yes, Alexandria, lots of places would charge multiple thousands of dollars for this. When we actually charge for training, we want to make sure that people not only get hired, but they get massive promotions and they have really good career accelerations. And that's why we built our career development program. We view certification as about 10% of the process. And the other part, we also understand that certification does help you get an interview. And because the interview is super important, we try and make sure that everybody has the certifications. We also understand that, there's a lot of things you need to learn: emotional intelligence, executive presence, and we want to give you free certifications so you don't have to waste any financial resources doing it. We like to do our certifications like this as in a live interactive forum because we want you to be able to ask questions. We saw some Udemy type courses where basically people bought training and they couldn't ask questions. I couldn't learn that way, and I would never want anybody to have to learn that way. So we do as many of these as we can for free. That's why we do them. So we will put a link to our training if everybody's interested, and then we will get back to the content at hand. Okay, William Wallace, why a /21 instead of a /22? The /22 would cover from 192.168.0.0/24 all the way to 192.168.3.0/24. But we were looking for a mathematical way to cover 192.168.0.0 all the way to 192.168.7.0. And in order to do that, we need to borrow an additional bit. And to do that, we need to go from a /22 to a /28. Leupold, I think we're going to have to get you a video on intro to subnetting. So Chris from my team. Chris, please take note of the people that need access to a video on intro to subnetting, and we'll make sure that we take care of that. Chris, send for the intro to subnetting. People like Leupold is one of our students. Shakula looks like he's got some questions, so make sure you take a list. Leupold just joined us yesterday, so we're pretty sure that he'll learn it real soon, but we want to make sure that nobody has any time waiting to learn anything. Okay, so let's go start talking about the cloud and your VPC. So, what is the VPC? Let's start looking about the VPC and the components of the VPC. So this is going to be a pretty heavy-duty section, the components of the VPC. And in here, we're going to start talking about routing and routing tables, fun stuff. We'll talk about internet gateways. We'll talk about an egress-only internet gateway. We'll talk about NAT instances and NAT gateways. We'll talk about elastic IP addresses. We'll talk about VPC endpoints. We'll talk about VPC peering. We'll talk about network access control lists. And we're going to talk about security groups. So, we'll take care of these things in this section. First and foremost, we're going to begin with a routing table. And when you actually sign up for a VPC, or you start using the cloud, you get your virtual private cloud, which is basically your own virtual private data center. And normally, you'd have a bunch of routers and switches from Cisco or Juniper, and they work great. With AWS, what's going to happen is they're going to give you a virtual router. Now, because it's a virtualized router, it's theoretically high availability, which means it shouldn't be going down and it should be working great. So it's going to be a virtual router. And the virtual router, just like any router, is going to help determine the path to get your traffic from point A to point B. That's it. So when you do this, they'll build a map. And previously I showed you what it looks like, but it's going to look a little different in AWS. Basically what you're going to have is you're going to have a route that's going to be it's going to have a route that's going to say this route is local, meaning directly connected. Here's a route, here's how you reach it. Here's another route, but here's how you reach it. And here's a default route pointing to your internet gateway. Now look at this. Look at these two routes. Look at this 192.168.0.0/16. Now, look at the 192.168.1.0/24. both. The 192.168.0.0/16 would also technically include the 192.168.1.0. But why? What is different? 192.168.1.0 is much more specific than 192.168.0.0. So you can have two routes in your routing table with overlapping subnets, the aggregate router, the /16 and the /24. And the router is going to always use the most specific route. So if you've got two routes that are overlapping, but one's more specific, routers take the most specific route. When it comes to traffic engineering, and that's coming, that is the fun spot, and we will be doing a lot of it. So let me know you heard me and comment most specific route below. So now let's talk about building the map. Now when we're building the map, we're going to be using a routing protocol, BGP. And the routing protocol that's going to be building this map in the routing table, whenever you're going to be connecting information, is going to be coming from BGP. And AWS lets you use BGP in a lot of different places. Now, the BGP that we're actually talking about is going to be eBGP, or exterior BGP. And you will be using BGP to do your direct connections. You will be using your BGP in order to connect to multiple entities. You will be using BGP for VPC peering. You will be using VPC for remote access type VPNs. You are going to be using BGP for everything. Everything in the cloud is going to be using BGP. And the way your routing tables are going to be built is they're going to look like this. You're going to have these data center and the cloud. So typically speaking, this is the way it would look. So let's assume on the right side of this, you've got the underlying network for AWS, because they're all designed this way. They typically have what's called an interior gateway protocol, which is almost exclusively OSPF, or intermediate systems to intermediate systems, for internal routing and network layer reachability information, as we call it. And they typically run eBGP or exterior BGP to other external providers. That's how organizations exchange information between the data center and the cloud. Now, so internally an IGP, or an interior gateway protocol, externally eBGP or exterior gateway protocol to connect to them. Now we're kind of at a point, as I'm ready to go to the VPC things, that I kind of had a thought. We're going to be talking about BGP everywhere. How many of you have worked with BGP? Could you let me know? Say, I've worked with BGP. And if you've not worked with BGP, let me know I've not worked with BGP, because I have the opportunity to start and talk about BGP for approximately 45 minutes, which I think could be a massive improvement to your careers. But I don't want to do it if you've all worked with BGP. So let me know, say, I've worked with BGP or I've not worked with BGP, and then I'll determine whether I should discuss BGP before moving on to the remaining VPC things. I want to make sure you get the best experience, so help me help you. So I only heard from 5 people. There's 140 some people on this call. Okay, so. Okay. Okay. I've only heard from about 50 of the 150, but what it looks like is people have not worked with BGP. Because BGP is such a critical routing protocol, would you like me to stop, take 45 to 60 minutes, cover BGP to make you guys all some pretty awesome cloud architects? Because if so, just let me know and I'll do that right now. Otherwise, I'll continue to just the AWS only stuff. If you want BGP, just tell me, because I'll do about 45-minute good intro to BGP right now, and I think that could be pretty helpful for you all. Okay, let's do this. Sounds like everybody wants some BGP. We'll do this. We're doing the advanced networking from an architecture perspective. How can you design stuff you don't understand? Let's do some BGP. BGP is fun. So BGP, everybody, one of my favorite topics. By the way, I've spent over 10,000 hours working in BGP, so I absolutely love it. So BGP it is. So let's talk about BGP. What is BGP? BGP is an exterior gateway protocol. It is a protocol that you use to connect to external entities. So inside of your entity, you use an interior gateway protocol. Exterior to organizations, you use BGP. BGP is an external gateway protocol. That's it. When you connect to external, you do it. So BGP is a routing protocol. What makes it so special? It's scalable. Routing protocols are like the GPS in your car. The GPS in your car tells you how to go to point A to point B and it reroutes you. BGP does the same thing. BGP is a scalable routing protocol. And it's a routing protocol that's designed to connect you to external entities. And in the process of doing that, it enables you to truly connect to lots and lots of different environments. So let's talk about this routing protocol. It's a dynamic routing protocol. A static routing protocol, you would have to manually say route. Whereas with a dynamic routing protocol, you don't. You just configure it and it starts learning. Kind of like the machine learning, the adaptiveness, and the AI of the world. Routing protocols did this stuff 30 years ago. They determined how to get from point A to point B. Awesome stuff. So routing protocols are dynamic, and they're going to build a map called the routing table. Now, when we're talking about BGP, it's different than other routing protocols. Normally, routing protocols identify each other with like a hello. I exist, hello, I'm here. And they form a neighbor relationship and they exchange routes like OSPF. Not BGP. BGP does not use multicast to discover its neighbors like OSPF, for example. You have to tell it who its neighbors are. So when I'm using BGP, it's using unicast between two hosts and you manually specify them, which means it's secure because you're manually specifying sender, receiver, and you can authenticate the BGP messages too, and you will. BGP, because it's a session between the locations, needs to be reliable. If I sent routing information and the person didn't receive it and I didn't know if they didn't get it, they might not know how to get to the destination. So BGP is reliable. What do we use for reliable transport? TCP. So BGP is unicast, unlike the rest which are multicast, and it uses TCP. Now it also uses TCP port 179. BGP TCP port 179. BGP TCP port 179. Why did I repeat this 3 times? Test question first, but more importantly than the test question, because I'm not real big on tests, I'm real big on function. If you've got a firewall and your BGP session is to go through the firewall and you don't open TCP port 179, it will never work. And trust me, I have seen more people mess up BGP because they didn't understand to open the ports on the firewall. More problems I've solved than organizations did that. TCP port 179. BGP is used because it is scalable beyond belief. I can connect to an internet service provider, pick up 750,000 routes, and I'll get them, and I can handle it in the router. Can't do that with any other routing protocol. Not only can I take in these millions of routes, I can very carefully share them with the people that I want them to. So fantastic. Lots of flexibility here. BGP is fantastic. So it's used for scalability and tunability. It enables you to customize things beyond anything you can possibly need. BGP is cool. BGP customization. So you can literally say one route preferred on one link, another route preferred on another link. You can tune it like you couldn't imagine. That's what BGP is cool. So BGP uses this thing called a finite state machine. So for those of you guys that are software developers, it'll make more sense. Basically, you've got one thing that goes around in a cycle and different things that can happen. BGP is this TCP-based connection thing. And because it's this TCP-based connection thing, it has to send a session between 2 locations. First thing that happens is the session comes up, and there's several messages that are exchanged in between the peers. The first message is something called an open message. What happens is you basically configure your neighbors, basically source, destination, and on the router, it would be like router BGP 65001, neighbor 172.16.1.2, remote autonomous system, whatever. So that's how you're setting up the session. When the BGP neighbors basically say, hello, I exist, welcome, they basically send an open message. And in that open message, they send up their BGP version, like version 3 versus version 4. their autonomous system, their identifiers, which is the basically the loopback address or whatever address you've chosen to use as your BGP identifier. And that's basically how the BGP speakers identify each other. Now, this is a little dry here, and it's a complicated protocol, but it's going to help you in your career, so bear with me a few minutes when we cover it. Now, you send an open message to basically, welcome, 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 this is who we are. Now, when you've got a TCP session, you've got to keep the session up. You can't just leave it as an empty session forever and expect it to stay up. So routers send a message called a keep alive to each other, which basically says keep the session open. But the keep alive does something else. It verifies the router is still there. So, you know how you're using a load balancer and they're basically running a health check to the servers? Are you there? Are you there? Are you there? And the servers respond, yes, I'm here, and they stay as part of the rotation. And the load balancer will basically, the load balancer will remove them if they don't respond to a health check. Same thing, the keep alive is ways that you can determine that your BGP neighbor is still there. So open, establish the session. Keep alive, make sure everything works. If the neighbor doesn't respond to the keep alive, just like a load balancer, it gets removed from their location and the session will be taken down. The next kind of message we'll talk about between them is something called an update message. What is this? So we got two routers, they establish a relationship, they're now peers. They're sending information periodically to make sure they're all up and running. BGP says, I learned a new route. Let me go tell my neighbor. That's what gets put in an update message. So you learn a new route, you update your neighbor. You lose a route, you get rid of it. That's what's going on in an update message. Basically, you're saying is what's going on. So the last message is a notification message. So this is not a good thing. So when you're dealing with notification messages, if something bad happens, you're notified. Hey, by the way, session's closed. So open. Basically, your sessions come up, they exchange all kinds of things, autonomous system numbers, BGP version numbers, hold times, BGP identifiers, that kind of thing. Then they maintain the session through a keep alive that says, I'm here, I'm here, I'm here. If one of the things doesn't respond to the keep alive, it gets removed from the location, just like DNS with a health check or a load balancer with a health check. Then in your BGP message, you just send an update. Learned a new route, got rid of a new route. And that update's going to have a lot of information. It's going to include like your route origin, the AS path, next hop, what have you. And then finally a notification. If things don't go well, not a good sign. And that's when you get an update. So, keeping what's going on here, I had mentioned that BGP forms a neighbor relationship. And this is where this ugly finite state machine comes in, but that's okay, you can learn it. So, when you're working with BGP and you're on a router, and you're looking at the route and you're doing like a show IP route and you're looking at the routing tables, and then you're looking at a show IP BGP and all of a sudden you don't see stuff, what's going on? So when you're troubleshooting these things and you're actually working, for example, with a router and you do like a show IP BGP neighbor because you're not getting routes, you want to figure out what's going on. And when you're doing the show IP BGP neighbor and you're looking at the neighbor, it's going to be in one of these states. Idle, connect, active, open sent, open confirmed, or established. Now, what you want to see is established. If it's established, routes and messages are going to be sent. But if it's not established, you've got problems going on. So let's talk about, what these states actually are. First, we'll talk about idle. When you first turn on your router and you just enable BGP, it starts out in an idle state. This is initial. This is basically where your router is just waiting for the TCP session to get established. This is completely normal. The second you just turn on the BGP on your routing protocol. Instant. It's supposed to happen this way. But if this does not connect, it'll stay idle. That's a bad thing. So it's supposed to start this way. Now, if you misconfigured BGP, it's going to go back to idle. If anything is wrong, it's going to go back to idle. Idle happens either in the initial or something bad happened and it goes back to idle. So when you're looking at it and evaluating and troubleshooting it, if it's initially idle, okay, but it should transition to open. But if it doesn't transition, you got a problem, go figure it out. The next phase is something called connect. So if you initially try to send a message and it's connection, BGP will process that open message and things are going to go well and it's going to transition to open sent, which is awesome. This basically means your BGP thing came up, you sent your open message, it's now open sent, and things are getting really great. Now at this point, you're going to wait for a connection. Now if the connection becomes unsuccessful, things are going to transition back to a state called active, which is not good. And if it goes to active, it's going to keep retrying. Now, if it goes to connect, good. And if it doesn't, it's going to go back to idle. So as you can see, things should go from idle to connect to open send. And then hopefully open confirmed and established. But if they don't, they always go back to idle. So if we're at idle, you got a problem unless it's initially. So we talked about what happens with connect. And then let's talk about active. We talked about things, if you can't get your connection, it goes to active, then it's going to retry to connect. And if it does, great. If not, it goes back to idle. So now open send. We talked about you send your message, you go from idle to connect, you send your packet, it hears it on the other side, it goes to open send. All is good. This is what's supposed to happen. And if the open message is sent to the other side, if anything goes wrong, you'll go back to idle. But if things go right, you're going to go to open confirm. And what goes on in open confirm? The BGP process gets a keep alive from the far end. Now you're now at open confirm because both people are there. Now you hit an established state, and when these things are established, they start exchanging routing information. So let's talk about it. How does it work? You start at idle. Idle things, nobody's talking to anybody. From idle, assuming if things are good, you go to connect. If you send that message and it connects good, it goes to open sent, then you get a response back, open confirm, you're established, you exchange rails. If anything happens along the way, it'll try another stage. So if you're in connect and you go to send a message and it doesn't work, you go to active. From active, you're going to try and resend. If it resends and it goes through, you go to open sent, which will go to open confirm and transition to established, you're good. But if it doesn't, you go back to idle. So when you're in active or you're in idle, things aren't working. So that's what you need to remember from a troubleshooting perspective. Now, this is some pretty heavy-duty BGP for an introductory level BGP. So we're going to talk a little bit about the attributes. Then we're going to tune it together and have some real fun. So bear with me for about 5 more minutes of this academic challenges. Apologies, this is hard stuff, but you can learn it. You can all be great cloud architects. This is part of the job, so make sure we all get it. So since we know how to how the BGP forms a relationship, well, I told you that people are using BGP because you can tune it. And because you can tune it, you can do lots of cool things. So let's start looking at the things that are actually tunable in the attribute-wise. So, no, actually, I don't want to talk about, I don't want to give you this, I think. So when you're actually looking at these BGP attributes, let's talk about them, because when you know the attributes, you know what we can tune. So BGP messages, command line. So William Wallace, most of the stuff for people like me is done in the command line. The good news for you guys is when you're doing it with AWS, it will spit out a router configuration for you that you can cut and paste into your router, but it may not be optimal. So you may actually need to know how to do this. For people like me that really love this stuff, there's a book called Internet Routing Architectures by Bassam Halabi. Sometimes he goes by the name Sam Halabi. CCIEs like me have been using this book for, well, probably 30 years now. But let's just say 25 because I feel better about it that way. So let's talk about these BGP attributes. Every message that you get in BGP, every time you learn an update from a neighbor, is going to have certain things in it. And we're going to cover what these things are. First, we will learn the origin of the route. What is the origin? It's how we learned it. What does that really mean? Did we learn about it because it was part of our internal network? Did we learn about it via BGP? Or did we learn about it via some other way that we're not sure? The next attribute that we're going to look at is things like AS path. What happens is it's a path vector protocol that's going to determine how many places it went through. So the path will be something that will determine the best route to the destination. So, all things being equal, the shorter the path, the better. So all things being equal, the shorter the path, the more preferred the route is. Makes sense, right? If you've got a 100-mile trip to somebody's house versus a 50-mile trip, the shorter the path makes sense. Now, you might not want to use the shorter path. Why not? What if the shorter path is on dirt roads? But the faster path is on a road that has nobody there, and you can drive your car legally at 200 kilometers an hour. You might take the longer route because it's shorter. Well, the same thing with internet routing. You want to be able to manipulate the path based upon it. So the path determines the number of internet service providers happens, but you can tune the path. The author's name is Sam Halabi, and the book is named Internet Routing Architectures. It's an old book, but all CCIEs are still using it. So the shorter the path, generally speaking, but you can tune it. The next thing is the next hop. Remember I told you routers basically look at the world in terms of next hop? Meaning go out this interface, go out this interface, go out this interface, and that's why I made weird kind of movements to pretend that I was a router that had like 40 arms. Same thing, BGP, next hop. Here's the thing with the next BGP. You could learn a route but not reach the next hop, but that means you can't reach it, so it won't be put in the routing table. The next thing, which was a Cisco proprietary thing, but apparently AWS supports it now, as do a few other people, is weight. Routers prefer the path with the largest weight. What does this mean? If you want to traffic engineer your thing, modify the weight. I'll show you what that means in a second. The next part of it is, now we're going to give you the algorithm. Here's the algorithm. Prefer the path with the largest weight. Meaning, weight first. If the weights are equal, prefer the path with the largest local preference. Again, I'll show you what that means and how to tune that. If the local preferences are the same, prefer the route that was originated on the router. We'll talk about what that means. If the local preference was the same and neither route was locally originated, prefer the route with the shortest AS path. Okay, what does that mean? I'll show you in a minute. If the AS paths are the same length, prefer the lowest origin code, meaning IGP, EGP, what have you. And then when that is the same, that's when you start getting into funny things. So the next thing would basically be, prefer the paths with the largest med. And then after that, that's when it gets really funny. Like if the med's the same, prefer an eBGP route over an iBGP route. And then if your routes are still equal, prefer the path one with the shortest next hop path. And then then we're going to get into the funny business so I'm not even going to cover that. So let's look at how we traffic engineer our traffic via BGP. If we're looking for simple and arrogant, this is what you're going to do. In this particular environment, let's say you have two direct connections to AWS. And you want to load share across your two direct connections. If you don't do anything, basically what's going to happen is you're going to have a primary link and you're going to have another link. And your data could be going off, coming over the top link and coming back in the bottom link. Now, why do we care if you do something like that? If you're doing that and your traffic is going in one link and out another link, what can ultimately happen is you can get what's called out of order traffic. Meaning if your traffic comes in one place and comes out another place, you're going to find yourself in a position where you could be losing data. And if you're losing data or you're getting out of order traffic, that's not in a situation where you really want to be. So what we're talking about over here is we need to prioritize one link over another link. We have to. So what are the best ways to do this? The best way to do this is basically to put a more specific route on one link and a more specific route on another link. And by doing this, we'll be able to prioritize traffic. So let's look at this top link. 172.16.0.0 is more specific than 172.16.0.0/15. Why? Because it's got a longer subnet mask. 172.17.0.0/16 also is more specific than 172.16.0.0. Is that obvious to everybody? Does everybody understand how the /16 subnet masks are more more specific than the /15 subnet mask? Could you guys please let me know that yes, I get this, or no, I don't get it? Because this part is critical for the next part of traffic engineering. You guys can let me know in the comment section. Okay, so I see one yes, I see one no. Let's try and look at it this way. The longer your subnet mask is, the more specific the route is. So if you've got two routes and one's a /16, it will be more specific than the /15, assuming it's the same overlapping information. If we have a /20, it'll be more specific. So let's do this. Let's make ourselves a new slide and let's work some through together. So let's take these two routes. I'm going to ask some of you guys from the crowd. So let's say we've got a 192.168.1.0/24, a 192.168.0.0/16, and a 192.168.1.0.0/30. Which is the most specific route here? Now let's say my destination IP address Let's put my destination up here. If my destination IP address is this, which is the most specific route? Route A, route B, and route C. Which is most specific? So, excellent. It's the /30. And yes, BGP equals Border Gateway Protocol. Absolutely. Good job, guys. So let's do another one because I want everybody to get this. I don't want anyone to miss this. Let's say now, which is the least specific route to this A, B, or C? What's the least specific route? C, exactly. Okay. Now what's the most specific route? After you guys tell me so the /16 is the least specific route. Now what's the most specific route? Okay, you guys told me the least. You did good. A would be the most specific. C would be the least specific. You guys did great on that. So. Okay, we're getting the most specifics. We're getting the least specifics. Now, let's do a little CIDR thing real quick. 172.168.1.0.0/16, 172.1.6.1.0/16. Anybody know how we can? Anybody know what we can do to summarize these two routes with a single route to supernet them, which is what we're going to be doing in BGP. If I wanted to put this and this into the most specific single route for both one of these, if I wanted to summarize both of these routes, what would it look like? If I wanted a single route to include both of these subnets. Yes! Flash 15. We're borrowing an additional subnet bit. Good job, everyone. Now, let's have a little more fun with this whole subnetting CIDR thing before we move on. 172.1.2.0/16 and 172.16.3.0/16. Now, let's come up with a summary route for all of them. Both the subnet and the subnet mask this time. Guys are doing good. Real good. Making me happy and proud. It's going to be a different subnet now that we've got four. Now that we've got four that we need to take care of. Now we're getting into slightly different. It's not going to be a /15 anymore. One of you got it right. /15 covered 0 and 1, but it doesn't cover 2 and 3. So, good job, Allie. So, /14, because the /14 is borrowing 2 additional subnet bits, and a /14 will give you all 4 of these. Slash 15 was 2 because it's 0 and 1. Slash 14 gives you 0, 1, 2, 3, 4. Great job. You guys are starting to get it. Now, what if we did 172.16.4.0 and then 172.16.5.0, 172.16.6.0, and 172.16.7.0. Now what would it be? Because, slash 14 gave us 0, slash 15 gave us 0 through 3. So if 0 and 1, so let's look at it this way. 0 and 1 bar is one subnet mask, and these two can be aggregated as a 172.16.1.0 slash 15. Now, we can aggregate the next two and bundle them from 0 through 3 with the slash 14. 2, 4, 8. So what's going to be one bit less than 15? I mean, less than 14. One of you got it. Well, it's going to be a slash 13. So what this tells me is we need to provide some subnetting training, and we will come up with some subnetting training for everybody. Not going to necessarily fit real nicely in a advanced networking course, but what we're going to do is, so keep doing the slash networking course. What we'll do is we'll create an intro to networking training session. We'll stream it and we'll make sure everybody does it. We'll do it on YouTube or Zoom, and we'll invite everybody that's been part of this. So make sure that you let us know that you're here. If you're interested, put subnetting, please. You may have already put it. Chris from my team is going to aggregate it. What Chris does is he basically looks for things that people need help with. And yes, we can do a subnetting boot camp. Happy to do so. Chris is going to copy information down and make sure that he collects information. So let's make sure we give you guys the information that you need. The rest of these will be super easy for you guys to understand, but these will be on the challenge and stuff. So let's get back to fun BGP manipulation. So we can do two things in order to make this thing work. We can put the more specific, the best way to load share and the simplest and most elegant way to do it is as follows. Basically what you do is you take two routers and you put a more specific route on one link and a more specific route on the other link. By using a more specific route on one link, it becomes the preferred link. By using a more specific route on the other link, that becomes the preferred link. And by having multiple preferred links, we can load share. So basically by doing it this way with this exact environment we're talking about, the top link has a more specific route for 172.16.0.0/16. So this route will be taken to reach 172.16. Now on the bottom we have a 172.17.0.0/16. That will also be more specific. So for traffic destined from the data center, so when the cloud sends data from the cloud to the data center, it's going to use the top link for 172.16.0.0, and it's going to use the bottom link for 172.17.0.0. Now, what happens if either one of these links fails? That's why we have that summary address, or that 172.16.0.0/15. The reason we do that is in case the main link fails, we've got another route to promote reachability. So this is the most simplest and most elegant way to load share or traffic engineer your data in the cloud. But since a lot of people need to learn subnetting, understand this is here, go back to this. We'll set up some time to teach subnetting, and we'll do it real soon because it's a real important topic. So just understand how that works. More specific route, less specific route. Now the next way we can do this, and mind you, anytime we're dealing with BGP, we have to do this in both directions, both on and back. So you have to manipulate your policy from the routes you receive from somebody else, and you have to help them manipulate the routes that they receive from you if you want to tune it. But that's a pretty big topic. So the next way you can do these things is just very simply is adjusting the weight. What is the weight? The weight is something that's associated with the route that can help you determine if it's preferred or not preferred. So how do you do this kind of stuff? You adjust the weight. How do you adjust the weight? You just basically set a policy. So if you look at this here, the higher the weight, the more preferred. So look what's going on here. By tuning the weight on the top link, you have 172.16.1.0 with a weight of 35,000. Now, look at that link on the bottom. It has a 172.16.0.0 with a 32,000. Which is more? 35,000 is greater than 32,000, so the top link is going to be preferred one for 172.16. Now the bottom link has a higher weight for 172.17, and the top link has a lower weight for 172.17. So in this environment, by tuning the weight on one side, as opposed to tuning the weight on the other side, we've load shared across two equal cost links. We can tune it another way. Local preference. Why do we tune local preference? It's easy. What's so good about local preference? We can basically send a community to someone else for them to map local preference or what have you. But local preference, the higher the local preference, the more preferred the weight. No different than weight. We could basically just take the route that we learned and we can modify the local preference. Meaning, raise the local preference on the link you want. So what do we do here? The local preference on the top link is greater than the local preference on the bottom link for the same route. So top link is preferred for 172.16. Bottom link is preferred for 172.17. And you've got a backup route that's non-preferred. Of course, we could just change the AS path too. So when you learn a route via BGP, and when you learn a route via BGP, you get what's called the autonomous system path, which basically is hop, 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 all the companies it went through. So you can just basically make one path look ugly by what's called prepending or adding additional AS paths. Again, tune this. Make it look ugly. Make the one route that you want to take preferred. Make the one that you don't want to take look ugly and do the same thing on both sides, and that's how you could load share. Or, of course, you could just change the MED or the multi-exit discriminator. Lower MED, preferred path. Higher MED, less preferred. So, change the MED or the metric to which one you want. Top link has a lower MED for 172.16. That's the preferred link for 172.16. Bottom link, preferred lower MED for 172.17. Uglier MED for 172.16. That's how your traffics are. So, all right, I bombarded you guys with about 200 pages worth of BGP materials inside of a few minutes. So, wow, we did that. So let's just look at it this way. Last thing, we're going to talk about BGP, and then we're going to get into more fun stuff, but we'll take a break and answer BGP questions. BGP is going to be required whenever you use a direct connection, so you must know how to use it. BGP has all these tuning options. We talked about tuning the MED, the AS path, the local preference, adjusting the weight, more specific route. You can tune it any of these ways. All this is covered in internet routing architectures, and if you come back to this, it'll make sense. And I made a couple of BGP videos for this, and we're going to be releasing a very strong BGP paper next week for everybody to use. Should be next week. Worst case scenario will be the week after that. It will be a big, extensive BGP guide, so you will know how to manipulate traffic. So if you desire that, send it down. Let it know that we want the BGP book, and we'll get you at least a very good BGP document next week or the week after that. Just let us know. So when you're dealing with AWS, it supports weight, local preference, AS path, just like any other good routing implementation. And just remember that AWS's BGP implementation is like junior, intro to junior. They only take 100 routes. So it is nothing like what you would typically deal with. It's a junior BGP implementation. So you're going to have to do your addresses wisely so you can do some route summarizations. Okay, so we're going to get talking about internet gateways and all these cool things, but we just did a lot of talk on BGP. So in case anybody has a BGP headache, and trust me, I've had a whole lot of BGP headaches in my life until I found out I love BGP. Who has questions moving forward? Does anybody have any questions moving forward? Chris, we'll get you a BGP document. We'll make sure that happens. We've got a nice one that's been pretty planned. I think the BGP will actually be easier to understand from the document than it actually will be from a training course, because that's the kind of thing you really need to look at and go back to a couple times. So we'll get you guys some good, strong BGP training very quickly. Okay, so while we're here, before we get into internet gateways, does anybody have any BGP questions that we didn't answer? I know we covered it quickly. Okay, so Gopal asked a question with regards to administrative distance. Administrative distance is a Cisco only thing. Um, and when you're using administrative distance, typically speaking, the Cisco routers have determined that certain routing protocols are more valuable than others in terms of accuracy. So it's determined that eBGP has a value of 20 and iBGP has a value of 200, which basically means believability. That is just a Cisco thing and is not really relevant in terms of AWS. It is not really relevant in terms of any other router for that. So it's just regards to just Cisco. So it's just a way that Cisco routers use it, and you can tune administrative distance. And that's only if you learn a route via OSPF and BGP, for example. Which one do you prefer? MTU values or maximum transition unit really has nothing to do with BGP. Realistically speaking, it's how much that you can actually send a packet on a LAN. Derek, thank you so much. Really did try to put some effort into making some good BGP videos for people, so thank you. And I'll definitely have that BGP document coming soon. So now let's move on to internet gateways. So an internet gateway is going to be a highly redundant, highly available way to connect to the internet. So according to AWS, they say there's no bandwidth constraints or performance limitations. There's no such thing as no bandwidth constraints or performance limitations, but that's the way they like to describe it. And the internet gateway is just a router that's going to connect your network to the internet. Now, when you're connecting your router to the internet, using an internet gateway, when you're connecting your VPC to the internet, you have to understand this is real internet access. And what I mean by real internet access, I mean you are really connected to the internet. And I'll talk about ingress only, egress only, and bidirectional internet access. But when you're using an internet gateway, you're getting true access to the internet, which means you're really on the internet, which means your systems are on the internet, which what that should tell you is they're hackable, easily hackable when they're on the public internet. So an internet gateway gives you real high performance connection to the internet. Why would you use an internet gateway? You might have web servers that need to be reachable on the internet. That's when you're using an internet gateway. How's the internet gateway work? You basically attach it to your VPC very simply, and you just create a default route which basically says all unknown traffic, send it to the internet gateway. That's it, unknown traffic. The default route looks like 0.0.0.0. That's it, default route. Your internet gateway has to have a public IP address. Why? Because it's sitting on the public internet. And remember, when you're using an internet gateway, your systems are publicly available. So what does this really look like? Let's say you got a bunch of EC2 instances. Let's say you've got an external IP address that's placed on your load balancer's external IP address, which connects to the virtual router, which then has a default route to the gateway. All your unknown traffic is going to go directly to your default router, to your internet gateway, to the internet. And you can see you're having a routing table. You're going to have your locally connected subnets, and then you're going to have a default route which goes to the internet gateway. All unknown traffic is attached to the internet. That's how you set up a web server. That's how you set up any kind of front-end web services in the cloud through your internet gateway. That's full communication. Let's talk about partial communication. Let's talk about egress-only internet gateways. Now, there's two kinds of egress-only internet gateways. Actually, three kinds that AWS has. They name them all complicated, ridiculous, funny things. What does egress mean? Exit. Egress means exit. So, egress-only internet gateways only allow for exit-only traffic and the return. So, egress-only internet gateways in AWS terms only refer to IPv6. Now, when you're dealing with IPv6, there really is no concept of public and private IP addresses. They're all public. So, when you're setting up an egress-only internet gateway, it's providing external-only access to IPv6 in the AWS cloud. So, an egress-only internet gateway is only allowing outbound traffic, and it's stateful. So, what's going on here is egress-only internet traffic goes out, and its return traffic is allowed in, like a firewall, but no exterior traffic is going to be allowed in. So that's the way an egress-only internet gateway works. It is 100% exterior only, and that's moving forward. So Before we move on, JBGP is not proprietary. It is an open standard specified in an RFC, and it's been around for about 30 years. Cisco does have some proprietary enhancements to it, just like other people do, but it's not proprietary. And you'll be able to watch this later on YouTube. We're recording this, and it'll be on YouTube. So you can share it with any friends you desire or watch it later. So this is going to be recorded to YouTube. So since we talked about an egress-only internet gateway being egress-only for IPv6, let's talk about the other types of egress-only internet access, which AWS causes different things. The next type of egress-only internet access is a legacy thing which AWS no longer recommends, and it's called a NAT instance. And basically what a NAT instance does is you create a custom, it's basically an EC2 instance, it's a virtual machine, and it translates your private IP addresses into a public IP address. So basically what happens, you set up a NAT instance, it translates your private IP addresses into a public IP address, and then you give that a default route to the internet gateway, and your traffic works perfectly. So your traffic goes out and comes back. NAT instances only allow egress only, which means it allows your internal traffic to go out to the internet and come back from the internet, but your systems are not reachable from the internet. So where is this useful for? Let's look in this environment. Let's say you've got servers and you want them to go to the internet to update their patches, for example. Fantastic, this is great. Servers go to the internet, they update the patches, great. But you don't want them reachable from the internet. So this is what's referred to egress-only internet access. AWS doesn't call it, they call it a NAT instance, but a NAT instance lets you go out and come back, but it keeps you isolated from the internet. So, but a NAT instance, in order to use it, you see you've got a NAT instance, you've got an internet gateway. It works. It's a legacy way. AWS doesn't recommend this anymore, and we don't either because of the complexity of using it. Here's what AWS recommends instead, a NAT gateway. And in reality, a NAT gateway is far simpler. Basically, it's a fully managed NAT service. It's redundant, so you don't have to worry about needing backups of these things, and you create it in a public subnet. And basically what goes on, you set up a NAT gateway per availability zone. It enables your systems to reach out to the internet to update their operating system, and it allows the return traffic to come back. Perfect. So if you get a test question, what do you have to do to let your systems reach out to the internet and update their operating system but not be reached? What's the preferred way? It is with a NAT gateway. NAT gateway is the preferred way of traffic on the internet. That is the optimal way to do these things. So these are what's going on as the NAT gateway. So what does a NAT gateway look like? In actuality, it is simple and elegant. You basically just set it, oops, didn't mean to do this. You just basically set it up, and when you set it up, you go from your basically private subnets to your NAT gateway to the internet. Egress only, meaning systems not hackable from the internet, but they are reachable, but you can go out to the internet to get updates, but you're not reachable. So let's look at your three alternatives. Alternative one, internet gateway. Use an internet gateway with a public IP address. You're completely reachable through the internet, in and out. This is where you're going to put your web servers. This is your demilitarized zone, where your public services are, using an internet gateway. Egress-only internet gateway. When you're using IPv6, you want to go out to the internet, and you want your return traffic, but you don't want to be publicly reachable on the internet. NAT instance. EC2 instance that does network address translation, translates a public address into a private address. That requires an internet gateway. It's egress only, meaning you can go out to the internet and your return traffic will allow back, but nothing else. That's your egress only. That's your NAT instance. NAT gateway, all in one device placed in its logical high availability. Basically connects you to the internet in a single device. You go out to the internet and come back, but your systems are not reachable from the internet. So now you know how that sort of works. So now that we're talking about all these other components in your VPC, let's start talking about network interfaces. So anytime you put a card in a server, it's to connect it to the network. And when you're dealing with virtual servers, you're going to deal with virtual network interfaces for the most part. So an elastic network interface is as follows. It's a virtual network interface that's basically going to be attached to your EC2 instance. By default, there's going to be an elastic network interface created the second you launch an EC2 instance, and it's going to be ETH0. That's going to be your ENI or elastic interface. Now, let's say you want to place your systems in two subnets or multiple subnets, then you're going to have to add elastic network interfaces. Now, for low security environments where people are setting up bastion hosts, they would use one of these things in the public side and one of these things in the private side. We don't recommend Bastion host. We recommend using secure access to your systems over your direct connection or a VPN, not a Bastion host. But for organizations that are not set up properly, that have to use a Bastion host to access their system, they're going to put two subnets in. Well, maybe on the outside, they enable SSH, which is kind of a no-no, but they may be doing that. And on the inside network, they'll enable access to their web server. That's how you would set up a Bastion host. Two setups, elastic network interface. But you might have a server that you want on 3 subnets for performance purposes. You'd add multiple elastic network interfaces, just like you've got real servers that exist on things. So now you know what an elastic network interface is. It's just a virtual network card that you stick in a computer. So, what about an elastic IP address? When you are on the internet, you need a globally routable public IP address. Public address, not a private address, the public address. Now, typically speaking, in order to get these public addresses, what you'd have to do is you'd have to get one. You'd have to register for one, get your autonomous system number, get your IP addresses. You typically have to register in order to get these addresses. Now, when you're with AWS, they make it really easy. They have a pool of public addresses called elastic IP addresses. And when you need a public IP address, it is simple. You're not going to Aaron, you're not going to Ripe, you're not going to anybody to register these things. You're basically just borrowing an elastic IP address. It gets used by your systems as long as you need it. When you're done, you don't need it anymore. It gets returned to AWS. This is the most simple and elegant solution. This is one of these things that makes the cloud beautiful because it's just so darn easy. We love this. So that's what we're kind of referring to here. So going on with this, you get an elastic IP address. You are borrowing, just specifically borrowing from AWS, a public IP address. So what does it look like? It looks just like this. You basically have an elastic IP address that you're borrowing directly from Amazon. And when you're done with it, you give it away. You put that, and basically it could be on your load balancer directly in front of your web servers, and now they're publicly reachable because we've got an internet gateway. Now remember, they are publicly reachable. Publicly reachable means hackable. Publicly reachable means hackable. So if you're going to do this, you are going to need a lot of security. And we'll talk about how to secure systems in depth throughout this process, but not right now. So now we're going to talk about this concept of endpoints. And endpoints, actually before we cover endpoints, you guys doing okay? Do you guys need 5 minutes to ask questions? Let me know before we discuss endpoints. You guys have any questions on internet gateways before we go over to endpoints? I don't see any questions coming up for endpoints, but I just wanted to make sure, prior to discussing endpoints, to make sure I see one no, which makes it look like you guys are doing okay. I just don't want to leave people stuck. That's why we try and check in so often. So, okay, thank you, Green Logic. Thank you, Guy. I'm going to keep going then. I know what it's like where people buy a course and then they can't ask questions. I would never want to be in that position. So even when we do free training, I would never want any of you guys to be in that position either. I just don't think it's a great position. Rob, is the EIP assigned to the gateway or the EC2? Okay, so the internet gateway is going to need an external IP address, but you're also going to need an external IP address on anything that needs to be reachable as well, such as your web servers or your load balancers. So you'll put an external IP address on your load balancer typically in front of your web servers as well. So let's start having some fun talking about endpoints then. So there are times where you want to connect to another service or another VPC. Now, one of the benefits of the cloud is really this kind of great thing, that things scale easily, and because the other people are on your cloud, and because every time you're using a public IP address, including a NAT gateway, it's still going to use an elastic IP address. And I use router symbols because, it's a virtual router, so I use router symbols. There are AWS symbols, but I'm a routing and switching person, William Wallace. So when I'm dealing with a router, I use a router symbol, and it may or may not be the AWS symbol. So that's why I do it that way. Makes the network engineers and architects like me understand it. Plus, I don't really draw my own pictures. I draw napkin sketches and I hand it to the graphics people on my team. So one of the privileges of being around for a long period of time is you can have other people diagram your things for you. And when you work as an architect and you move up to the senior levels, at some point you're going to have other people that will actually do your things for you. Like when I worked at Cisco, I would design my systems, document it all on paper, and then I hand it to somebody else to professionally draw it for me. So that's why I'm used to doing it this way. So whatever is convenient to try and graphically represent it. So, but when you're dealing with an endpoint, it's because you want to connect to a public service or somebody else. Look at it this way. Let's pretend you wanted to create connections to 1,000 remote locations. And you're welcome, PNU, and I'm really grateful. So we want to connect to 1,000 remote locations. What people like me do is we get 1,000 routers, we buy 1,000 WAN connections, and we set up this really complicated routing, and it works perfectly, but it's expensive. What if your 1,000 people are all running on the cloud and they're all connected to the cloud? You don't have to build a network anymore. Wow, this is awesome. Because you don't have to connect to the network anymore because it's all built. Wow, this is really exciting. All you need to do is just connect to the other people. And how are you going to connect to these other people? You are going to do it through an endpoint. By using an endpoint, you're going to be able to connect to other organizations across the AWS backbone, which means private, it means secure, and it means high performance. Unlike the internet where you can't guarantee performance, when you're using an endpoint, you're riding the AWS network for which they can do QoS policies to make sure your traffic gets through. So, endpoints are this awesome way to connect to multiple entities on the over the AWS network. This keeps you from needing to buy WAN connections. It keeps you from needing to buy LAN connections. It basically lets you use their network. So, endpoints are good. They give you high performance, low latency, good security, and low costs. So what's it all look like? Let's just take the most simplest use case. Well, let's say S3. If we weren't going to use an endpoint and we were in our VPC and we wanted to connect to S3, we'd have to go out to the internet, across the internet, and back into AWS. Now let's look about this from a routing perspective. First, internet routing is best effort, meaning no guarantees of your data, which means low performance compared to direct connections. So by going to the internet, we've got to go to the internet, we have to deal with internet performance. Where if we could just ride the AWS network and go straight from the AWS VPC to S3, your communication's better. But it's worse than that. AWS charges you for everything. So they're going to charge you to send your data out to the internet and then come back in the internet. So by using the internet, you've got to pay more to have lower performance and less security. So then you'd have to encrypt your traffic. So that's a disaster. So you'd create an endpoint to basically just connect your VPC to S3 over the high-performance AWS network. That's the whole point of endpoints. They are awesome. They keep you from needing to build your own network because you're going to ride Amazon's network. So when you're creating endpoints in your systems, you've got two options. You've got a gateway endpoint and an interface endpoint. And endpoints are highly available virtual devices that scale. So these are really great ways to connect to other services. So let's talk about the endpoint types. So, endpoint type 1 is a gateway endpoint, and this is going to be really a high-speed, high-security access to an AWS service. And it's going to do this by placing a route on the routing table. So think of a gateway as endpoint as basically AWS S3. And we'll answer your question. PNU, please bear with me. I will answer your questions as well as teach you how to definitely get a job when you're lacking experience, and Chris can send you some information as well. So please don't go away. I promise to answer that. So regarding your gateway endpoints, they're high-speed, high-security systems to AWS services. And you create a route in the routing table. And what's going to happen is it's going to give you like something called a prefix list. And you're typically going to see your gateway endpoint to S3. And it's going to look like a PL, and you're going to have a bunch of numbers. And that's what you're going to see in your routing table. So let's give you a look at what a gateway endpoint would look like in action. So let's say you've got your data center and we've connected to the cloud over, say, a VPN in this case, and we want to provide shared services to our S3 buckets. What we could do is we'd create an endpoint to the S3 bucket, and then we would connect our data center, and the data center would be accessing the endpoint through our wide area connection, which in this case happens to be a VPN. So this would enable the VPC to basically connect to the S3 bucket and then connect it back to our data center. And so let's talk about, gateway endpoint security. So basically, if you're going to be using this, remember some tenets of routing. If you don't have a route in your routing table, you couldn't possibly reach it even if you desired. So don't share a route so then that you to things you don't want. So just by filtering routing information, you can really limit your endpoint security. So minimize who has access to which information. And PNU will get to you shortly. So part of your security is just don't let the routes be available. And obviously you configure endpoint policies as well to limit who can access what. You've got all your IAM and other things. I'm just telling you, IAM's great, but if you don't have a route, you can't reach it. So definitely make sure that you have routes. The next type of endpoint is an interface endpoint. And this is really when you're going to connect to lots of different things, maybe an EC2 systems manager, Kinesis, load balancer APIs. This is going to be how you connect to other things. So also how you want to connect to other VPCs. So an interface endpoint is kind of different. When you're connecting to an interface endpoint, what it really does is it places like an elastic network interface in your VPC. So it's going to put it on a different subnet. So what's going on, it basically enables your interface to be part of the same network for which you're connecting to. And when you do this, it creates like an endpoint specific name. So an interface endpoint directly connects you to somebody else. And it does this by placing an interface in your system and using a service called private link. And what private link is, and excuse me, I may have to sneeze here. Okay, what? Excuse me. Excuse me. Excuse me. Sorry, I have this really great little cat, which I love my cat that I adopted recently, but I'm highly allergic to her. But, she follows me around the house and sleeps with me and my wife every night. So the cat's always around me. So apologies for the allergies. So anyways, you create this interface endpoint, and basically it uses a service called private link, which is basically creating a private line over the AWS network. And by doing this, you're able to connect yourself, thank you, to this VPC or this other AWS service over the AWS private net connection. Gives you lots of high performance, lots of private connectivity. Thank you again so much. And it's private, so you're creating an interface endpoint to reach another service. Restricts all traffic to the private line. And guess what? It does something called NAT, Network Address Translation. Why do organizations use NAT? Here's how we find people that are ready for cloud architect job versus just certified. NAT is used anytime you need to translate one address into another address, not just for the internet. Why does private link use NAT? Well, let me tell you. RFC 1918 specified some private IP addresses such as the 10/8, the 172.16 all the way to the 172.31/16, the 192.168.0.0/16. Guess what? Everybody's using them. So if you want to connect your VPC to someone else's VPC and you're using the same addresses, you've got problems. So when you connect your VPC to someone else's, you use private link. And it uses NAT to make sure that everything is good. So let's look at our endpoint options. Again, gateway endpoint, connect to S3, places a route in the routing table. Interface endpoint, connect to pretty much everything else. Creates an elastic network interface, so you're on a subnet. Creates a private link between you and everybody else. It's a single direction link, so if you want bidirectional communications, you enable them in both directions. And that's how you send your information from point A to point B over the private link connection. It restricts all traffic between your organization and the partner organization. Here's what it looks like. Basically, you set up your VPC, you set up your endpoint, and your devices basically connect to your endpoint, and that's it, and it runs perfectly. Private connectivity, high performance, high security, love it, great thing. Endpoints may be the primary, endpoints and auto scaling may be the two best reasons that organizations even move to the cloud. Only specifically for this. These two things might be the big enough reason in themselves to adopt the cloud. So now, here's where it could get a little potentially kind of confusing to people. Gateway endpoint, S3. Interface endpoint, other VPCs, for example. So what's the difference between VPC peering, which we'll talk about a lot more, and private link? A lot. So let's talk about the difference. When you connect one VPC to another VPC via VPC peering, that's VPC peering. It's quite simple. But when you're doing VPC peering, VPC1 and VPC, they're paired together, they can communicate everything. When you're using private link, it only allows access to one service. So if you need full communication between two organizations, you can use VPC pairing. But if you only need access to one little mini service, use private link. Now, when other would you use private link versus VPC pairing? Let's talk about this. For the following examples. With VPC pairing, you're dealing with many-to-many services, but private link enables you much more scalability. You can't do above more than 125 VPC pairing connections in AWS. But you have a lot more. You can do thousands of private link connections between your organization and external organizations. So because of that, VPC pairing scales much better. Private link scales better. So if you need full communication of everything, VPC pairing. If you need access to one service, use private link. Private link much more scalable. And the limits of private link are only related to the max throughput achieved by your load balancers or servers. So you've got a lot of scalability there. So some more differences. When you're doing VPC pairing, it would be great if you're all using different IP addresses. But remember I said most organizations use overlapping IP addresses, private addresses. So VPC pairing does not work with overlapping IP addresses. You would need to use NAT. But private link automatically does that, and overlapping address space with VPC pairing is not supported. So that's another thing. So let's stop here for a second. We covered the interface endpoints, we covered the gateway endpoints, and private link. Now we're going to talk about VPC pairing and shared services PVCs, and I'm going to get there in a minute. But we just covered a lot of stuff really quick. I saw there were a couple questions that were there, so I'm going to do this. We're going to stop, we're going to ask some questions. And so bring in your questions. I also saw some questions. I saw them from PNU, and I started to see them coming in. PNU, Mike, could you tell us where someone without experience in IT should start before getting into the cloud? Well, I would start directly in the cloud, PNU. Which cert should you go for before getting cloud certs? Thanks. So, PNU, what I would do is what I do with everybody else is we have a 16-week program where we take people from no background, and by the time we're done, we teach them everything they need to know to be a cloud architect. A cloud architect needs to know the network and the data center. So, we teach you the network and the data center as part of our cloud architect program, and then we teach you all the other skills that are necessary. So, I don't recommend you getting any other job prior to the cloud because they're not going to be related. A cloud, for example, a cloud architect is a systems designer. You have to know the network. So, certifications that we typically do with our people might be a Cisco Certified Network Associate or Professional, a Linux one, and the AWS Certified Solutions Architect Professional. It's the bare minimum certification as a general rule to get your first cloud architect job. When you don't have experience, it's not just enough to get certified. That isn't even close to enough. That is 10% of what's necessary. When it's your first job and you're lacking experience, you must work on your executive presence, your emotional intelligence, your communication skills. You must talk about presentation. You must work on your interviewing skills. All this stuff is critical. When you want to take a big job and you have less experience, you have to polish yourself up. You have to look so good that they can't help but hire you. So for the last 2 decades, when we've been helping people get their first tech job, and we never tell anybody, look, you need to be help desk first. We don't do that. We don't start people off with those types of jobs. We start people off with bigger types of jobs. Why? Time is money. The average cloud architect earns $600 a day in the US, and a good one can easily earn double that, easily, and much more than that. So don't waste your time doing things that you don't desire to do. If you desire to be on the cloud, work on the cloud. Learn the network, learn the data center. If you train with us, you will be in great shape because we have a system. It's a 250-hour training program from start to finish. If you're on your own, we'll be honest with you. Learn networking from Cisco. Learn DNS and load balancers from F5. Learn virtualization from VMware. Learn security from Cisco, Palo Alto, Checkpoint, and Fortinet. Lots of good training there. When you're done that, you're going to need to learn how to present like an executive. Jerry Weissman has some very good courses. They're a few $1,000s, but they're great. Speak Easy does it as well. When you're done that, you need to do some emotional intelligence training. When you're done that, some business writing training. If you're training with us, it's all included. But make sure you do that. And if you're training with us, great. And if you're not training with us, buy yourself a 16-core Xeon server with at least 128 gigs of RAM. And on that server, you got to learn the network and the data center. So set up VMware ESXi, set up some containers, build a firewall, build an open access VPN, set up Microsoft Active Directory, build a Linux Apache MySQL PHP stack. Build a cloud. I mean it. Build your own OpenStack Ansible or Nutanix cloud. That's going to give you some competency that you can show employers that matter. You don't need to start with junior level jobs. You can start straight with a great cloud job and get paid for it as well. But you got to have the skills, and those are the skills that are necessary. Chris popped a link to our training program. That's how we train people. For people that have questions about our training or desire to train with us, they can call us. We have people that answer questions constantly. We'll be a little slow this week to respond to voice calls because we've got this boot camp, plus we do the free training we do every morning, plus we've got a lot of students we work with on our own. But for anybody that's curious, then we answer that. So PNU, we answered your questions. eBay is a good place to buy servers for cheap. Having said that, GZ, my program is cheaper than the servers actually would cost you. But if you're not training with us, definitely get yourself a server. And eBay is a great place to find them. Sequoia, is there any requirement for Bastion host? Well, lots of people use them, but from a security perspective, they shouldn't be. So I wouldn't design anything with the Bastion host. I would do things properly, but lots of people still use them. Guy Wittenhouse, AWS only allocates public addresses to the client that asks for them, yes. They don't come naturally. When you're using private links and VPC pairing, you're going to have to create cross-account roles, Muhammad. And VPC is very different than NATing. VPC is your own private data center. NAT is what do you call it? NAT is designed to translate one address to another. Augustine, how much does a junior cloud architect make? You're dealing with about $120,000, $130,000 a year. A good cloud architect earns well over $300,000 a year. But I will tell you the difference because I've been architects of all schemes on the junior end and the senior end. The difference between a junior architect and a senior architect is the following. 90% of it is communication skills, presentation skills, executive presence, the ability to do ROI modeling. That is 90% of what's necessary to go from a regular cloud architect to the more senior side of it. The second side of it is knowledge. The people that are hireable and paid the most are the people that have lots of knowledge in a small area. We're experts. I'm a networking expert. I've spent 10,000 hours in BGP, 5,000 hours in PIM for multicast. It makes me an expert. It takes 10,000 hours in something to become an expert. I've spent my 10,000 hours plus in BGP. That's what it takes. So, you want to be an expert, you want to earn a lot, become an expert in something. And yes, William, our training course covers everything at about 10% of what it would cost to train on your own. So yes, we did it because we're a cross between a mission and a business. We're like a charity, and that's why we do all these free training courses. We know not everybody can afford it. And when we truly take in paid students, William, we want to know that basically we're giving them about 1,000 times more than they're paying us. We basically cover our costs. We cover our employees, we cover our technologies, and we can change the world, and it's something we love to do. So that's why we do this that way, but don't consume our training. But it's a one-stop shop, and there is a lot to learn PNU. But so the other way you can enhance your career as an architect, and we'll get back into the tech, is to specialize in an industry. Here's an example. I used to work in the service provider industry. I spent 10 years designing systems for internet service providers. Loved it. And then one day, I was designing systems for a bank, and I loved that too. Now, for those of you that don't know me, I used to practice medicine before I went into tech 25 years ago. And that's kind of a specialty. I spent 7 years in school for that. So here's what happened. Cisco decided they were going to start a healthcare consulting division, and I became the lead architect for healthcare. That's when my career did this. Why did it do it? They sent me for executive coaches. They sent me for communication skills training. They sent me for presentation training. And oh, by the way, I was an expert in healthcare because I could practice medicine. So that's what I was referring to. Oh, Gopal, we provide training and lab experience. Our students even build clouds. Like setting up an EC2 instance or an S3 bucket, nobody cares. But when you build a cloud and you tell an employer that, they care. Our students build their own cloud. They build their own AWS-like environment. So yeah, we've got labs, hundreds and hundreds of hours of training in our program. And anybody that's got questions in our training program can call us if you desire. Shakula, when do you use private link? Any example use cases? Yes. Shakula, you're in an environment, let's say you created a VPC and you wanted your VPC to connect to 1,000 partners. That's when you're going to use private link to connect to all 1,000 locations. If you want to connect to any AWS service that's not S3, you're going to be using private link. So pretty much you're going to be using interface endpoints and private link anytime you want to connect to someone with the exception of VPC pairing, Shakula. Trying to see if there's any more questions over here prior to going back into things, because I want to make sure we give you guys all the questions. I think PNU, here's my perspective of certifications before we move on. Certifications can help make your portfolio look better to get an interview, but certifications have nothing to do with you getting hired, only interviewed. 10 years ago, I would tell you get a lot of certifications and they mattered. Here's what happened a few years ago. Exam dumps popped up everywhere, literally everywhere, and made the value of certifications go really low, because you can completely get certified in a million things and know zero. So between the types of courses that you can buy for $10 that can teach you how to pass the exam and still know nothing, and exam dumps, it made certifications not that meaningful. So we picked the ones that really matter. So a good Cisco one, a professional one, and then maybe another one from the industry is typically for cloud architects. But certifications are based on exactly the job you want. If you guys want to tell us what jobs you want, tomorrow I will do a cloud architect career question and answer session at 9 a.m. Chris can provide that information. He'll pop it in the link. I will let you ask any career questions you desire tomorrow if you want. And then Thursday morning, we'll have a how to get your first tech job, cloud architect job seminar. And I will tell you every step necessary to get hired from the beginning. We'll do all this for free this week for you. So tomorrow morning, Cloud Architect Career Question and Answer Session. Thursday morning, we will have a free How to Get Your First Cloud Architect Job webinar. Chris can provide that information for that too for you. So hope we answered those questions. So, and William, I've done this for 20 years, helping people get their first tech job, and well over 90% of my students have gotten their jobs. I will tell you, we launched this program 14 weeks ago, based upon what I've done on a one-on-one basis for 15 years. Prior to even graduating my company, the 15th one of my students told me today they were hired. So 15 people that haven't even had a chance to fully graduate my program out of about 125 have already been hired. The remaining ones are very close. So I hope I answered your question there, William. Chris provided the link for tomorrow's session. I highly recommend you join us. You can sign up, that's on, and then the Thursday one's going to be on Zoom. That's a real fun one. So please sign up, everybody. We will get to transit gateways. That's part of something we're doing. The Slack group is only available for our professional development students, Augustine. So let's do a little more tech stuff for the day, because tech is cool and tech is fun. So let's definitely do some tech stuff. So let's get back to here and let's start talking about shared services VPCs. So let's say you're an organization and you're on the cloud. Now let's say while you're on the cloud, and I'm also going to provide our number for you while we're out in case anybody needs to talk to us or ask questions. So let's say you're on the cloud and you want to be a service provider. Say you've got a service that you want to provide to other people. And you want to create other people that are connecting to you. You can create what something's called the shared service VPC. So maybe you provide a service of some kind. So what happens, you're going to create a VPC. And then when you create the VPC, inside of your VPC, you'll place a load balancer, and the load balancer will be pointing to your services. So I'll give you a picture of what this is actually going to look like. Alonzo, thank you. Alonzo is one of my students. And what's going on here is, let's say you've got multiple VPCs. You basically set up this shared VPC and you point all your VPCs to the shared VPC. This enables you to pretty much basically set up an environment where inside of the cloud, all these remote locations can connect to your shared service. Pretty cool. What would this shared services VPC look like off of the cloud? You take your data center and you'd have to build all these really expensive wide area connections. So why do you not have to do this here? Because AWS has the network that already exists. So if you want to be a service provider, if you've got some kind of service, let me tell you, it's awesome on the cloud. Love this. Set up your shared services VPCs, set up your private link or VPC pairing to all these remote locations, depending upon what you're going to do. In this case, we're going to use private link. And poof, and usually going to use private link. You can connect everybody to your shared services VPC. And now you've built an environment where you can literally share your information with so many people. And You don't have to build your own network. So when people ask me, should I move this to the cloud, I always say, it depends. And where does the cloud shine? Auto scaling, which we'll talk about when we talk about more agility and business planning, disaster recovery, and the network. It's pre-built. So when you're in the cloud, you need less CCIEs like me and more people that maybe are at a CCNP level in terms of knowledge to do these kind of things. Huge savings in terms of cost, and it's really hard to find a guy like me that does nothing other than BGP. Here you can get someone that's got a mid-level person on networking knowledge and has some cloud knowledge, and they can do both rails. So that's why these things are going. Network engineers like me all had to learn the cloud because our jobs are kind of getting reduced. So for network people like me, learn the cloud. That's what we did. And that's why most of the network people that I know are all moving towards the cloud as well. So now that we understand what a shared services VPC is, we covered VPC endpoints. Again, this stuff's going to be up there so you can review it again. Look, this is can be a little foreign, so we're moving a little fast, but we're always around and these things can be viewed again. So now let's talk about VPC peering. VPC peering is another really great way. So VPC peering is a way that you can take your private network and connect it to other people's networks. Kind of cool across the AWS network. And thank you so much, PNU. So if you didn't have VPC peering, you'd have to buy private link and private line connections, just like we've done for years. But you don't have to do those VPC peering. Now, things to know when you're dealing with VPC peering is it provides non-transitive routing. Now, when we talk about non-transitive routing, I will show you what that means in a minute. Non-transitive routing means if I learn a route from someone, I don't tell it to somebody else. So if this is, I'm trying to find a place. If this is A and this is B and there's a C afterwards, if A tells a route to B, B won't tell it to C in non-transitive routing, which means C won't be able to reach A through B. And we'll show you exactly what that means. So when you're using VPC peering, it is not transitive, which means it is ugly. Ugly, ugly, just like IBGP, and I will show you how, and then we'll show you how to make VPC peering not ugly. So let's look at what VPC peering realistically looks like at its simplest term. Let's say you've got your organization, the 10.x, which is specified by the VPC on the left with the 10.0.0/16 address space. And then let's say on the right, you've got your VPC environment set up with the 172.31.0.0/16 address space. All this stuff is great. Everything's working, happy, good, wonderful, awesome. Now, that's one set of VPC peering. And this is really simple and easy. Why is it simple and easy? Because it's only one site connected to another site. Routing works perfectly. This is really, really, really smooth. Think about it this way. If you're on the cloud and your partner's on the cloud, all you have to do is VPC peering and you're talking to each other. Green Logic, this is different than loosely decoupled. We'll probably get to that at another point, but very different concept. Basically just connectivity across the AWS network. Now, AWS high-speed network, so it's not like using the internet. We don't need to use a VPN because we're using the AWS network. It's a private network. Because it's the AWS network, there's quality of service that's guaranteed and performance that's guaranteed. VPC peering is awesome. But remember, VPC peering is non-transitive. And I'm going to show you about that. So if any of you guys are familiar with IBGP and fully meshing your IBGP pairs, this is the same problem. And if you're familiar with BGP and IBGP and the route reflector environment, that's what we're going to have to do here as well. So let's talk about what it actually looks like and what I really mean by this. So let's pretend for 2 minutes we are not in AWS. And we created a hub and spoke environment. For those of you that are not familiar with hub and spoke environments, if any of you have ever taken airplanes and you've had to go through a hub airport like Atlanta or JFK or Houston or Dallas or London Heathrow or Dubai, what happens is when you want to reach a destination, you go through a hub. So if I want to go to my home in Greece, just visit my family, I go from Miami, which is a hub airport, I fly to London Heathrow. From London Heathrow, I take a flight to Athens, and then I visit my family. London Heathrow is the hub. There is no direct flights from Miami to Athens because Athens is not a hub. But when I go see Athens, I go to London, and from London I go to Athens. That's how I visit my family in Greece. So by comparison, that's the way hub and spoke works. So going through this, That would work perfectly. But the problem is when we're dealing with VPC peering, it is not transitive. And being non-transitive, let's look at it this way. We have VPC A in the center. In a normal world, like the airplanes that we're talking about, if VPC A is connected to B, C, D, E, F, and G, B will be able to reach C through A in normal routing, just like C will be able to reach B through A. But because AWS routing is non-transitive and routes are not exchanged, A will be able to reach C, A will be able to reach B, A will be able to reach G, A will be able to reach F, and A will be able to reach E, and A will be able to reach D. But B and C will not be able to talk to each other through A. So, realistically speaking, VPC-A has communication with everyone, but nobody can talk to anybody. Now, if you want this to occur this way, this is great. You've got a high security environment automatically done for you by AWS's routing limitations because they assume you don't know better. But what if you want everybody to communicate with everybody? Well, then, and PNU will get your answer as well on the next break. So then, if you want everybody to talk to everybody, here's what's going to have to happen. You're going to have to fully mesh them. And what do I mean by fully meshed? Everybody is going to need a connection to everybody. Well, obviously, this isn't going to scale. And if anybody doesn't know why this is going to scale, I'm going to tell you quite frankly. When you determine the number of connections that have to connect to each other, when you've got a lot of people, they rise exponentially. The formula is n times n minus 1 divided by 2. So with 3 VPCs, you don't need that many connections. It's no big deal. Because it's going to be 3 times 2 divided by... So now, let's imagine you have 20 connections, or 10 connections. 10 times 10 minus 1 equals 90 divided by 2 is 45. Now 20 connections, 20 times 20 minus 1 divided by 2. Now you're getting a 90 connections. So if you've got 30 VPCs, you're going to have 435 connections to fully mesh, connect everybody to everybody. That won't scale. That'll be a nightmare. Could you imagine setting up 435 VPC peering connections just to have 30 people to talk to everybody? It's crazy, so it doesn't work. So, for those of you guys that are familiar with BGP and route reflectors, we came up with something called a route reflector. And what a route reflector would do is it would remove the concept of the non-transitive routing. So with AWS, when you need to do this kind of VPC peering, you have two options, CloudHub and Transit Gateway. They're two versions of the same thing. I'll explain to you why they're the same thing from a networking perspective. From the pure AWS perspective, they're a little different. So I'll explain the subtle differences between them for you, but you need to know this. If you've got multiple VPCs and you want to connect them to each other, what you need to do is you enable HubSpoke, CloudHub. And what CloudHub will enable you to do is it will enable you to use a hub and spoke environment. And by being able to create a hub and spoke environment and still enable people to talk to each other. So let me show you what's really going on here with CloudHub. When you're using CloudHub, and CloudHub is explicitly for VPNs, to connect your environments, it could be data centers, it could be VPCs, what have you. So what's going on is you're basically going to peer your locations. So by using it this way with VPN CloudHub, you're going to run what's called eBGP or exterior BGP. And CloudHub is going to break the AWS non-transitive rules, which means that New York's information will be passed to the VPC, which will also be passed to the London location, which will also be passed to the San Francisco location. Because routing information is going to be exchanged between these subnets through CloudHub, everybody will be able to reach everybody, which means New York will be able to speak to San Francisco through the VPC, and London will be able to speak to New York through the VPC, and London will be able to speak to San Francisco by enabling CloudHub. So what CloudHub does is it breaks the non-transitive routing that AWS put in place for you because they assumed that if you didn't understand transitive and non-transitive routing, the entire internet's traffic would go through you. So understand that CloudHub enables you to create a hub and spoke environment. But CloudHub only works with VPNs. So let's say you didn't want to work with VPNs and you wanted to work with something different. You wanted to work with private lines. Then you couldn't use CloudHub, you'd have to use Transit Gateway. So the Transit Gateway is effectively the same route reflector environment that's being used by CloudHub, but Transit Gateway is used explicitly for creating hub and spoke environments that allow for transit. So when you're doing this in this environment, everybody will be able to reach everybody through hub and spoke. So actually, you know what? We've got a couple more things that are part of this VPC before we get into the next concept. So let's just keep motoring through them, and I'll answer some questions towards the end. A couple minutes left, everyone. The next part of what we're dealing with in the VPC is something called an access list. Now, this is easy. For those of us that have ever worked on routers, and we put an access list, which is a non-stateful list, which is just basically a packet filter, which basically looks at your source and destination address, protocol, and port number, and says allow or deny traffic. That's what you can do. So tomorrow what we'll do at some point is we will map out a real high security architecture that's used in the cloud environment. It won't really be part of the AWS Advanced Networking, but I feel like it's important for all of you to know how to create high security, high availability environments. And since we're running our course any way we want, and we want to make you guys great cloud architects, we're going to teach you how to do it anyway, even though it's not part of the curriculum. So remind me to do that tomorrow. Talk about how to build high availability, high security, high performance systems with you guys. So one of the ways you keep your systems secure is you keep traffic out of the subnets that you don't want there. So on a router, in a normal environment, you'd put an access list on a router that would say, keep this traffic from going to this subnet. Totally perfect. Now, in this particular case, you don't have a real router. You got a logical router in the cloud, so you're going to create something called the network access control list. And on the network access control list, what you're going to be doing is you're going to be basically saying which traffic is allowed in and out of a subnet. So, a network access control list in AWS blocks traffic from going into a subnet. I'm going to say this again, it's a test question. Network access control lists protect a subnet. Security groups, which we'll talk about later, protect a host. Network access lists control a subnet. Security groups protect a host. Now, when you're dealing with network access lists, two things. They are not stateful and order matters. By non-stateful, it means they don't track the state of the connection. Let's look at a firewall. If I'm behind a firewall, and I am, and I want to go to the internet, here's what happens. My PC goes to my firewall, and my firewall says, Mike is initiating traffic out to the internet, let it out. And when the traffic comes back, say I'm going to the Cisco website, I'm always on the Cisco website researching something, and I have been for the last 2.5 decades, so I go to the Cisco website, and then the traffic comes back from the Cisco website to me, and when the traffic comes back, the firewall says, look, the traffic is, Mike initiated the traffic for Cisco, Cisco's sending the traffic back to Mike. Mike's traffic is allowed back through the firewall. Why does the firewall know? It's stateful. It's watching everything I'm doing. It's watching everything that's going through it. So the firewall knows to allow my return traffic out and my return traffic back. That's why I don't have to put any policy on the firewall that says allow in, because it already knows. It's smart. Access lists are not smart. They're very dumb. They're not paying attention to anything that's going on in the system, so they don't know to allow my return traffic because they're not stateful. So stateful does not mean apply in both directions. Stateful means tracking the state of the connection. Network access lists are not stateful, so you must enable them in both directions. Now, going back to these non-stateful access lists, order matters. And what do I mean by order matters? As soon as the packet hits a rule, it's going to be permitted or denied, and that's it. So, order matters. So, let's look at it this way. Let's assume we didn't know anything about it, and we created a rule 100, and the rule 100 says, deny everything. And then after that, we had a rule that says, permit web traffic. Well, in theory, that would work great, but it won't, and here's why. The rule 100 says deny all traffic. The traffic's already dropped long before it even hits rule 110. So this is not the way you build an access control list. So if you want to do it right, the proper technique is as follows. First, you don't need to deny anything unless you want to for specific purposes, because there's an explicit deny. Instead, just permit the traffic you want in. So if you've got a web server, only allow port 80 or port 43 in, and that's it, and nothing else. You'll be more secure. Inbound and outbound, that's what you need to do. And what does it look like, architecturally speaking? Architecturally speaking, what you can do is you can see how this, you've got an internet gateway, you've got a router. We're protecting the subnet with a network ACL. Now, we're going to protect the hosts with a security group. So in combat, you're going to use both. It's not an either nor, but a network ACL protects the subnet and a security group protects the hosts. So now let's talk about a security group. It's kind of like a host-based firewall where it only allows certain traffic inside of a host. And that's exactly what a security group actually is. So a security group is like a host-based firewall. A security group is part of the AWS environment. You set it up to only allow traffic inside of your host that you absolutely desire. So host-based firewall inside of these things, basically to allow services to your thing. A good security architecture is going to have a combination of network ACLs and security groups, with the network ACLs protecting the subnets and the security group protecting the instances. Now, security groups allow or support allow rules only. So, just say the stuff that you want allowed and everything else is going to be blocked. Now, the good news about these security groups is they're a little smarter than the network ACLs. They're stateful. And because they're stateful, you only allow them inbound. Allow port 80 traffic in, allow the return traffic out. You don't have to do it, it's stateful. So you only have to apply them in one direction because it's stateful, because it knows to allow the return traffic. So what does it look like? I'll show you. Going back to here, network ACLs protecting the subnet, security groups protecting the hosts. Now the last topic we'll talk about today, and then I'll open it up to questions, are VPC flow logs. So for any of you that have ever worked in Cisco networking, there's the concept of Cisco NetFlow. And Cisco NetFlow would let you kind of see the traffic that's kind of moving through your system, so you know how to capacity plan, troubleshoot. Well, you need visibility into your network, and you're going to have a lot less visibility into your network in the cloud than the data center. Because it's not like you can create what's called the span port on a switch where you can mirror what's going on in a VLAN and then put a protocol analyzer or a sniffer and figure it out. So you need a lot more work to do these things in the cloud. So that's the concept of the VPC flow log. And the VPC flow log is similar to Cisco NetFlow. And basically your data and your flow information can be sent to CloudWatch or S3. And we'll talk about much more of those things later. But it'll basically be useful to diagnose connection problems. Maybe you've got a security group that's blocking traffic. Maybe you've got a network access list that's blocking traffic. And when you set up your VPC flow logs, you're going to have a lot of information that you can capture. And your flow log is basically going to take your capture, your traffic, and it'll let you know whether it's accepting it, rejecting it. And you're going to be able to look at basically your interface, your source address, destination address, source and destination port numbers, protocol packets, and it's going to look like this. Actually, we borrowed this directly from Amazon, so we've listed the site of where we've taken it from. Basically, you're going to have your account ID, your Elastic Network Identifier, you're going to have your source address, your destination page address, your protocol, and your port number. And this is really where you're going to get a really good feel for the traffic that's going through things. So you can see what traffic's accepted, what traffic's rejected. So that's what you're going to use flow logs for. So we've covered a whole lot of topic for today. So I'm going to answer some questions, any questions that you desire. So I see the first ones. Do you have to explicitly allow packets to leave the region? That's going to be based upon your routing. You can't go anywhere if you don't have a route. So if you have a route for your traffic to get out of the region, you'll still be going there. Can load work in conjunctions with prior to internet traffic? So you wouldn't really design it that way. So you would design it more of a high security environment. We've got, we can design a high security environment now if you guys want for a few minutes, or we can save it for another time. Before we get into this, do you guys have any more questions for me about this topic? So I'll wait for that. In terms of PNU, can I comment on CCNA knowledge? Is it enough? No, it is not enough. Regarding certifications, CCNA is probably good enough for the cloud computing people. CCNA does not cover BGP. CCNA is very light on the routing. CCNA is kind of an introduction to things, but it does look good on a resume, and it'll make sure you understand subnetting real well. It'll make sure you understand VLANs covered real well. It'll make sure you understand the basics of routing and more specific routes and less significant routes very well. It'll teach you about .1 queue tagging. So the CCNA covers a lot of the fundamental components as in a good introductory level. The CCNP knowledge is really what's necessary to actually do any work in networking, including this. Thank you, Gopal. Thank you, Tejo. So what I will do is this. If anybody, tomorrow we are going to have, and I'm going to drop the link of this if I can find it, we are going to have a completely, bear with me, free question and answer session on YouTube Live. Bear with me. I will give you the link to this right now. Just give me one moment. Tomorrow is the 15th, right? Oh, tomorrow's the 14th. So tomorrow we will be doing a Cloud Architect career question and answer session for any career questions you may have. We will do that. Bear with me. I'll paste the link to that. Okay, so actually, Green Logic. Let me try and give you some guidance and maybe try and save you some time to your career. Okay, so regarding the link I just sent is for the free training tomorrow. Regarding the Cloud Practitioner, Green Logic, we strongly recommend people skip the Cloud Practitioner exam whenever possible. The reason we recommend people skip the Cloud Practitioner exam whenever possible, it is basically near impossible to ever get a job with the Cloud Practitioner exam unless you want to be a sales rep. The AWS Certified Solution Architect Associate exam is nearly the same level of difficulty of the Cloud Practitioner. AWS makes all these exams hard, no matter what. So it'll typically take you about 2 months to do the Cloud Practitioner, and it'll still take you 2 months to do the Certified Solution Architect Associate. Given the average Cloud Architect earns $600 a day, and there is zero benefit to doing the Cloud Practitioner, by skipping the Cloud Practitioner and going straight to the Certified Solutions Architect Associate, you've saved yourself 2 months of time, which is worth $24,000 on average for the average Cloud Architect. So strongly recommend skipping the Cloud Practitioner, going straight to the Certified Solution Architect Associate. Understand that's not enough. The professional is kind of the bare minimum level of cloud certification necessary, but it will not be enough without knowledge of the network, the data center, presentation skills, communication skills, and those other things. All of it is mine, and here's why. When people ask me if certification is enough, I say, let's take a doctor. I said, certification training teaches you the name of the service and how to configure it. So imagine training a doctor and saying, these are the pills that exist and these are the dosages of the pills, without teaching the doctor how to diagnose the patient, ask the right questions, assess the patient, or do anything other than pills. You'd be running into a doctor's office and they'd give you their favorite pill without knowing what they're using it for. Certification training is the name of the service and how to configure it. As the cloud architect, you got to meet with the client. You got to ask the right questions, business goals, legal goals, communicate with them. Then you got to evaluate their systems, understand how they all work, and then move those systems to the cloud. How can you do that if you don't understand the systems? Like the doctor that doesn't understand how to diagnose, evaluate, or examine a patient. So it's the same kind of thing. So skip the practitioner, go straight to the associate, but you still need cloud architect training. Train with us, train with somebody else, but make sure you get cloud architect training if you want to be a cloud architect. And we provide a tremendous amount of free training, and we are always happy to do so. We just want you to understand, whether you're with us or without us, the way to get to your goals as fast as possible and as cheaply as possible. And that's why we created our training programs. So I will do this. I will see if anybody else has any more questions. And that is a salesman, sir. And that's the reason they're teaching that. So, and if you guys have any questions about your career or want to work with us, we have we're leaving you our phone number here. Tomorrow, we've got a lot of fun things coming. At 9 a.m., we have the completely free Cloud Architect question and answer session, for which we've got you. After that, we've got the, We've got the free boot camp. Thursday morning, we're going to have the free How to Get Your First Cloud Architect Job webinar. Chris posted the link. We'd love to see you there. Thursday afternoon, we're going to go back to this. We're going to do this training on Friday. And it sounds like you guys want more free boot camps. I'll do for more free boot camps, and I'm happy to do that. Anything we can do to raise the level of the Cloud Architect community, it's an honor and privilege to be with you guys, and I don't take it lightly. But if you want to be a Cloud Architect, try and get some Cloud Architect training with us or with somebody else. We provided the links to our training, but I want to make sure you all know how to get there. So, any questions for me before we close out the day? While we're waiting, if you had fun today, can you type Cloud Network Architect? And if you've enjoyed this video, please leave a like. Please subscribe to our channel. Hit the bell to be informed of new free things that we do when we do them. If you've enjoyed this and you're willing to share this with somebody else, please let other people know about what we're doing. We're really trying to elevate the Cloud Architect community so they know what to do and can be hireable. People did it for me when I started networking many years ago, and I loved it. So please help us share and spread the word of the free mission that we have to provide free certification training throughout the world. Shakula, it's totally dependent upon the use case. If you need to use, if you're using VPNs, you use CloudHub. If you're using private lines, you use Transit Gateway. Portia, great having you. Shakula, great having you. GZ. William, love that name. Saw the monument in Scotland. Always happy to have you all here. Any more questions before we close the day? Thank you, Kay Terry. Appreciate everything. And if you know anybody that would like access to any of this, please share the links to this and let us know. Thank you all, everyone. It's been a real honor and a privilege to spend the afternoon with you. I will see you all tomorrow. If you want to let us know how you found us, that's great. We want to be in the places that you're at so we can provide the access to the most up-to-date, highest quality training information. And look out for that BGP book, that BGP document that's coming next week. We think you're going to like them. And as Chris from my team said, if you are in the position to basically fill out this form to let us know how you found us, please let us know. Thank you all so much. Such a privilege, and I'll see you all tomorrow. Take care, everybody. Take care. You're welcome, PNU. Ned, thank you all. Talk to you soon. Wonderful, thank you. You're welcome.